GeoCat repository first. Oh, that is so bright. Okay, awesome. Okay, thank you again, everyone, for attending, and thank you, Katie, for that great introduction to ESDS. Hopefully, some of your familiarity has gone up a little bit. Yes?
I don't think you're sharing the screen.
You might have stopped the screen share. If you go to the meet and then share at the bottom.
Thank you. Saw it up there, so I was like, what? Okay, so a little bit about myself. My name is Julia, and I've been here at NCAR for 3.5 years, I guess. So I've done some work with the ESDS community and Project Pythia, which Katie mentioned, and I'm basically here today to make sure everyone understands the Binder workspace and feels comfortable with the work environment before we move forward with today's content. So briefly, everything's in Python today, which is a high-level interpreted open source language. If you are new to Python, Heather will be leading the breakout session on Python basics, which will be great and enriching for you. But I'll just say that high level means that a lot of commonly used functions and data structures have been provided for you, so you don't have to get in the nitty-gritty of memory use and things like that. And interpreted means that you don't have to compile your code, again, making it easier for you. Potentially making it your code a little bit slower, but at the end of the day, less time struggling with development is a good thing for scientists. And one thing that makes Python really unique and something we have embraced here at NCAR is that it is open source. So it's free, and if you have a problem, it's likely that someone else has already tackled it and provided that solution somewhere. So this is great, and we're going to go over some tools in Python today hopefully can help solve some of your problems. So first, I want to encourage everyone to open the Binder session for whichever breakout group you've chosen to join, because it could potentially take some time. But we do have a break after this before those sessions begin, so I'll post those links in the chat. But first, we're going to open the one for the GeoCat tutorial for the majority of this tutorial session. So if you can navigate here to the GitHub repository for GeoCat tutorials, and you'll see that we have some local installation instructions, which I'll just point out will not currently work if you have an M1 processor on your machine. And we're going to encourage most people to use Binder. So once you get here, go ahead and click the Launch Binder button. And that's going to start spinning over here. So while that's launching, let's navigate to the Project Pythia Jupyter and Binder instructions so that we can kind of get the groundwork while this spins up. So if you type Project Pythia, it should bring you, oh, okay, never mind. It's .org, not .com. At the top nav bar, we're going to go to Foundations. There's other resources if you need to get used to everything on the Project Pythia portal, but we're going to fast track you over to the Jupyter content. So basically, Jupyter Notebooks, like Python, are an open source application. This is for the web and allows you to share specific notebook files that contain executable code, LaTeX, Markdown, plots all interspersed. So instead of writing a long script and at the end you get your result, you're able to break your computation down into smaller pieces that tell a better narrative. So this can be easier for following each step, making sure that everything's on track. It also makes for great scientific blog posts when you go through your data analysis, then your results, things like that. It just tells more of a story. So what Jupyter does, if you're running it locally, is it launches to a web browser, but still uses the power of your machine to open the notebook, and you can run Python, R, or Julia. And this is great because it uses basically HTML and all your web browsing things to render nice and prettily. What we're going to do today with Binder is this remote execution. So basically, your machine goes and talks to the Jupyter Hub, which could be on the cloud. I think Katie mentioned that we have Jupyter Hub on the supercomputers, HPC systems as well. So your workspace should look the same regardless of if you're working on your local computer, the cloud, or HPC. So it communicates remotely, and you can then run your code and everything from your machine, and it feels a lot less intimidating than when you had to run remote code all like in the terminal, and you couldn't necessarily see what you were doing if you're used to a nice user interface. So I'm just going to go check on Binder again, see how we're doing. Okay, it's still taking some time, so this is definitely why we're going to open them before we start the breakout sessions. Okay, so we're going to give a little breakdown of Jupyter Lab, and we can revisit this when we're actually in the Binder to make sure everything matches what you're expecting and what I've told you to expect. So this is the interface you're going to see. On the left, there's going to be a sidebar that's going to display all the different files that you can navigate through. At the top, you're going to see a menu bar that is similar to any other program you've run. And then you have a workspace area. So it's going to open up to a launcher where if you were running a code from scratch, you could click on one of these buttons here to open up an instance of Python 3 with the conda environment you'd like to use. But the thing about Binder is actually the environment is already built for you, and you're going to be opening a notebook that is already built and being able to run it and interact with the code on your own. And it won't change anybody else's instance of that code, so you'll get to explore in this sandbox that we've kind of set up. Okay. Take a closer look at the left sidebar. There'll be a launcher, but you also have the kernels that are running, things like that. Don't worry too much about this. Again, on Binder, that'll be helpful for anyone who's running it locally. Okay. And there is a terminal that you can access on Jupyter, and you can run your terminal commands. Another nice thing about Jupyter is that you can run terminal commands interspersed. So if you just put this $, you can double check anything. So at this point, I am hoping for this to run so I can give you the introduction to the GeoCat content. But since it's not ready yet, I can just show you on GitHub. Should be fine. Yeah. So I'm going to quickly glance at the chat and see if anyone is trying to run this locally and having any installation troubles. See? Okay. It looks like there's been some help in the chat and there's nothing outstanding right now. Okay. So we're gonna go into notebooks, and then into GeoCat comp, just GeoCat, and then overview. Thank you. Okay, so this mirrors what you're going to see in the binder workspace as well. Okay, so GeoCat stands for the Geoscience Community Analysis Toolkit, and it was established in 2019 to help with NCAR's pivot to Python, where we need to support a lot of the functionality that was formerly in NCL, support the NCAR scientific community, and any other atmospheric oceanic scientists that might be interested in these tools for computation, visualization, and all of the other great work that the GeoCat team does. Okay, so GeoCat aims to create scalable data analysis, and it's built upon these cornerstone technologies that are displayed here. So GeoCat leverages X-ray for better data input, output, compatibility, uses Dask for scalability, which is great for parallel computing and things like that. Jupyter, which we just talked about, Matplotlib and CartoPy are used as well as GeoCat Viz to create better data visualizations. And then we also have Numba and Data Shader here used for some other tools. I'm not as familiar with them as the rest of the team. But there'll be more on these tools, how they all interact, how GeoCat leverages them, and the GeoCat tools built upon them coming up later today. Okay. Okay, would you like me to discuss the structure or was? Okay. Okay, yes. So let's take a look at this. I don't think I can set it up locally on this machine. I also, my personal machine is an M1, so I cannot share what the local installation looks like, but I can walk you through the steps and some common challenges. So let's go back to the root of this repository. Okay. So the first thing that you're going to do to get a repository down locally is to clone it. So you can either copy this command, git clone, and then the HTTP link to the repository. You can click in any repository, this button, code, and then copy is a great way to get exactly the right URL that you need. So this is all in your terminal, in your favorite workspace. You're going to git clone it. And then you are going to cd into the directory that you just built through the git clone command. So make sure you're in the directory you want to be when you do git clone. So make sure you're already in your documents folder if that's where you want this folder to be nested, things like that. So you move into it, and then within it, there's an environment file, which we can go visit and check out in a second. So with all environments, you can build them from an existing YAML file that has every package that you need listed. And this saves a lot of time from installing them one by one. So you're going to do conda and create -f for file, and then the name of your file. And it's pretty standard for that file to be named environment.yaml in whatever repository you're looking at. And then you activate your environment with conda activate, the name of the file, which after you've created it, the terminal will output a line that says, this is the name, you can activate it with this, because you have to actually go into the file otherwise to see what it's called. And then finally, you'll launch with Jupyter Lab. And Jupyter Lab should look much the same as Binder. Oh. Okay. Notebooks, GeoCat. So here we are finally. So if you have this open, you should be able to move around it, do some stuff. So for example, you can open a new notebook and you can try various Python commands just to make sure it's running. And that should work. And so you can see that you have code in these different blocks in the output, and that it tells you kind of where you are at each step. Now, the thing to be careful about with Jupyter Notebooks is you have to run your cells in the intended order from top to bottom, and it will let you run them in any order you want. So if you say A equals 1, A equals 2, print A, it says 2. But you can also go back and rerun the cell and change the value of A. So this can be more complicated, but if you're reusing variable names and not careful about how you run them, you could potentially have unintended consequences. You can also run the entire cell, I think with this button here. Oh, nope, sorry, that's to restart it. But usually there's a run everything button. I don't see it right now, but is it this one? Nope. Oh, right here? Thank you. Selected cells, yeah, run all cells. And we go back to the order that the author of your notebook intended. Are there any questions? Okay, binder just started. Great. Okay. So now that you just got that binder started, let's get the other binders up and running so that we don't have to wait 20 minutes into the breakout sessions on basics, NumPy, Xarray, and data visualization. So you can have that set up and ready to go at the top of the hour. Or is it on an hour? Okay, so first, let's open the Python basics one. Where's that? Okay, or Heather, if you could post the link to your binder in the chat, that'd be great. That actually might be the easiest way to do this. If each session leader can post the link to their binder in the chat. Yeah.
My binder is just whatever's in GeoCat tutorials. Actually, anything related to GeoCat tutorials will be in there. Do you mean the binder for the Python basics?
Yes, the binder for the Python basics, the binder for Deepak's Xarray session, for Elena's data visualization, and for the NumPy session.
Yeah, I don't have a binder for that. I'm doing a live code demo.
Awesome.
But I can share that when we get into our breakout room.
Okay, you're golden. I just wasn't sure if they can all open a new binder in the GeoCat, a new notebook in GeoCat binder. That should work. So for the NumPy session, which I'll be leading later, you can get to that by NumPy in the back on Project Pythia Foundations, NumPy Basics, and then you'll see this Launch on Binder button in the top right. And if you click that, it'll bring you to the binder space that we will explore and go through the content together. And it should be ready by the time we all reconvene. Yeah, maybe. So that is admittedly the one kind of challenge of binder is that the environment seems to take a little longer to set up than locally. Well, maybe I spoke too soon. I got lucky this time. But binder offers so many great perks to running a tutorial. The fact that we can all be looking at the same code, the fact that we can run cells together and interact and change them and move forward. It's a great teaching tool that we're excited to use today. So if there's any questions, if anyone needs help setting up their environment, we're going to use the remaining of the time to troubleshoot with individuals. If you did not have any trouble, feel free to take a slightly longer break. And let me double check when we're reconvening at 9:45. So if you're all set, great. If not, I will see you for the next 20 minutes, and we'll see everybody in about a little less than 40 minutes. Yes.
Yeah, you showed the binder for NumPy, but for the other session, if for the XRA one, it will go. If I have to start, do I have to start the binder now? Okay.
This way? Yep. So thanks again for posting the links. That hopefully makes it easiest for everybody. So we have a matplotlib tutorial and X-ray. And thankfully, okay, this is a good sign for today, at least on my machine. Hopefully on everyone's machine, it's opening quick. But thankfully, you're able to preview the content while it's building as well. Yes.
Just to clarify, when we open a binder to close out of it, we just close the tab. There's nothing else you have to do, like close the session.
Yes, for binder on the cloud.
Okay.
If you were on HPC, like on Cheyenne or Casper, you need to actually close down the kernel, or else it's running in the background and charging you some money.
Right. But for these binder links, whatever ones we don't need, we can just close out of them and just go to the one we need for our breakout.
Mm-hmm.
Okay, great.
Yep.
Thanks.
Thanks for asking that.
Like in the session?
Oh, yes. Would you announce which room is in
Yeah.
which
So
session?
could you access to me?
Yep. So I'll go to the ESDS blog post. Okay. Here's the agenda for today. So up next are the breakout rooms. So if you're joining us virtually, you have access to the links for each of these. If you're here in person, Orhan is about to tell you where to go.
And then should be listed up.
Yes. Okay. I don't want to.
When it doesn't know, it just.
Yep. I'm not going to open my email on the
Sure,
screen that
let
I'm
me
sharing.
find it and-
Okay. Oh, yeah. If I go offline, do I need to start binder all over again? Or as long as the tab remains open, it should just restart. You will probably have to start binder all over again. If you leave a binder instance, if you haven't done anything on it in like 2 hours, I don't know the exact time, it'll get a pop-up that your kernel is no longer active and you'll have to restart and rebuild your session. So it, again, since it's using these cloud resources that are provided, there's things in place to make sure no one is using an expensive amount of computing power. So it will die if you haven't touched it. It'll die if you exit out of it or go offline. You should be able, for these instances, this binder, any changes that you have made Also, since it's relaunching from a static content, those changes that you made are also going to not be there on this binder instance. But if you're running it locally, you can save it and it should all still be there. Does that answer your question? Okay. Yep. Thank you.
And also click on the very top Google Meet links.
Google Meet links. Perfect. Okay, so Kevin, if you're here, when you double click a cell, you should be able to do a Shift Enter to run it. Now the import doesn't have any output, so let's run this one to get a clear answer. I'm going to type this in the chat in case you're not here. So I guess if you left the call, you won't see my chat response anyways. Okay, you're still in the call, so I'm gonna.
Yeah, I am still here. I'm trying to run the command. So double click and then shift enter.
Yeah, Shift Enter should work. You can also hit this little play button
Wait,
at the
I'm
top.
not seeing
Will run the selected cells.
what play button.
Right here.
Yeah,
Here, let me.
I tried that and it didn't work. So I needed some.
Is it possible that there was a pop-up that said something along the lines of like server connection lost?
I didn't see that.
Okay. I would try to open it again because that'd be my first guess of why it's not working for you. So here's the link again to Foundations, and then if you from there hit the binder button and reopen it. Oh, let me see if I can find anything like binder not executing cells. Yeah, my first guess would be to reopen it and make sure it didn't time out during the break. So
Well, it's responding to things that I'm trying to do, sort of. If it had doubt, would I get any response?
okay, I'm sorry, there was a lot of echo when you said that.
I'm getting a response from it. So does that mean that it is not timed?
Why is it echoing? He's not getting a response, but it's hard to hear. Is your computer muted? These two are both muted. Yeah. There's no audio option. Could you type your question in the chat? It might be a little easier while we figure out why there's an echo. Yeah, so I thought it'd be easier to be able to see the chat instead of going back and forth. Oh,
Is it muted?
yes, this one's muted and in companion mode as well. Okay, so I just got this server connection error and I hit dismiss. So I'm just gonna test. Oh, that's on the GeoCat one that we don't want to use. Anyways, okay, good. I was like, that was too fast for NumPy. Some responses from the Windows, so that means it's not timed out. What do you mean by some response? Like when you run a cell, it creates this result under it. This import isn't going to print anything. So you can also test if it's working. Just create a new cell and say like print 1, just to make sure you're printing something. Run a cell, we get no output, but the next cell gets the blue bar. Okay, can you confirm that the cell you are running is supposed to have output? Mm-hmm. Yeah. So down at the bottom, also, there's this Python 3 kernel. For me, it says it's idle because it's finished all execution. I'm going to go run a cell, and you'll see that for a brief time, it'll say busy. Okay, it was so brief. Let's try like wait, the wait function. Can I just do like that? Okay, it's not defined like that, but it should take it a little bit longer. Sleep. Sleep is not defined. Okay. Go to yeah. Okay. Yeah, I'll stop sharing, and Kevin will see if you can share yours, and then we can work on this together. The cell with line A. Okay, so like the one right under create an array of data, you create the array and then you print out A. So for me, it prints array 1, 2, 3, and for you, it's not printing anything. So welcome back, everybody, to the NumPy breakout session. So during this session, it's basically going to be led by you, the audience, and any questions that you have, anything that came up during the videos you watched or your own applications. So we are definitely going to use this time to work and make sure, like work with you individually to make sure everything is expected and not leave anyone behind. If no one has any questions, we're going to run through the Project Pythia NumPy binder that you've all opened. So we're just going to run through that in lieu of your questions. So feel free to interrupt, speak up, maybe comment in the chat instead of just unmuting yourself. But Kevin, I'm not sharing my screen right now because I am leaving the floor open for you to share yours so we can troubleshoot your problem together. Oh, you think it's working for you now and I should share my screen? Okay. That's great. Okay. Did anyone have any immediate questions that came up while they were going through the content, watching the tutorials, or maybe even going through this exact same notebook? So you can raise your hand, you can put it in the chat. If it's quiet, actually, I think this meeting is small enough that I think you can unmute yourself without creating a pandemonium. So I'll begin and I'll just stop once something I say inspires curiosity. So NumPy, it's like a fundamental Python package. It's one of the first packages that anybody learns when they're learning Python, and it allows for n-dimensional array objects. So the Python already allows for a list data type, and a NumPy array is a little bit more sophisticated. There's a little bit more that it can do for you than a simple Python list, but it's built on top of that. So first, we're going to create an array. We're going to go over some math with NumPy to kind of show what's so great about it, like what it has to offer, the way that it can automatically do broadcasting and things like that for you. And we're going to do a refresher of how to do slice indexing and things like that. So before we begin, you need to run the NumPy import cell to make sure that you have NumPy working for you. If anyone is having trouble here at this point, please speak up that you have your space open. The packages are importing. And to make sure no one else is having the same problem that Kevin was having, jump down and execute this cell where we create our first NumPy array. So it should have this red number. For you, it won't be 13. I've just already run a couple cells and it auto renumbers. And you should have some output. So to create a NumPy array, you use the command numpy.array, and then within the parentheses for the arguments, you can enter the first number, which is well, actually, here we've entered a list. So we entered the list 1, 2, 3, and we're converting it into an array, into a NumPy array. Now, there's some things that we can do and use NumPy to better inspect our new array. So we have a number of dimensions with .ndim. So this is a one-dimensional array. It only goes in one direction, but it has the shape of 3. So you'll notice that the shape isn't just the number 3. It's like 3 comma blank, and that's to account for other dimensions that you might have in a more complicated matrix that you're manipulating. And we can also double check our type. So as opposed to just getting the type of the object A, which I will show just for a second. So if you did type of A, you would get that you're working with a NumPy ND array. But a NumPy array dot data type, dtype, will show you what is in each cell, each element of your array is, for us, it is int64, so like 64-bit data type. So in a Python list, you can have a different data type for any element if that suited your fancy. You could have the word blue followed by the number 7, followed by a different object that you've created. But in a NumPy array, for it to leverage the capabilities that it brings to the table, it is designed to be used with numbers, and those numbers will all be the same type. So I mentioned multiple arrays. So here again, we are creating a NumPy array that is a list of lists that we're converting. And NumPy displays it like this. We have an array, goes 1, 2, 3, 4, 5, 6. And there's some great things that you can do with this. So just to compare, we have 2 dimensions. The shape should now show 2 numbers, 2 and 3. And now we have floats. So before, these were integers, you can see. There's no dot after them, they're just a number. Where here, it's dot. This little dot is indicating that we're working with floats. Okay. So you can create NumPy arrays without first creating a list, and you're going to do that with the arange function. So the one tricky piece I'll say about the arange is that it is exclusive of the last number, but inclusive of the first. So if you just enter a number, that's going to tell you how long you want your array to be, and it's going to start 0 indexed and move up. So you have 5 elements. So that goes from 0, 1, 2, 3, 4. So similarly, if you give it a start number and then an end number, it's going to start with the index 3, and it's going to move up, but the last element you're going to see is actually going to be 10, not 11. You also have this option to add a third argument, and that creates a step size. So when you go from 1 to 10, every other element, this is going to create just odd numbers for us. Okay, NumPy linspace or line space works a little bit differently. So let's see. So what it does is you give it the starting number and the stopping number, and then tell it how many steps you want. So for an arrange, you give the start number, the end number, and tell it the step size. Here we create step size. It infers it by how many steps you want. So it does a little math for you, and this makes it, this is nice if you don't actually care what these values are, or you know that you want to evenly split something up. It's nicer to not have to know what those sizes are. So this is 5 long, as we specified with the number 5. For this one, it might be a little, you can see that in order to do that, it actually includes the value 4, where arange would stop at 3. Well, since our step size here, you can see a clear difference is that our step size is bigger than our final value, where in a range, if you tried to do that, you would only get the first element 0. You would be given a NumPy array that's 1 element long. Okay, we'll make another one that makes better use of the step size by doing a little bit more complicated math than just finding the whole numbers for us. So when you go from 3 to 10 and you want 15 values, you're going to get every half number. Here's just another example. So again, I'll just point out that the line space, but when you type it, there's no E, is inclusive of both ends. And let's just count, make sure. There should be 11 elements here. 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let's do a little arithmetic to see what you can do with NumPy. So here we have a list with the range 5, 10. So again, we're working with the base data type a list that Python has, which you can create a list. Let me create this in its own cell first to demonstrate it a little bit. So I guess we're actually already printing it, so we don't need to do that. So when we just run this, you'll see that A, the list we created from 5 to 10, also exclusive of the last number. And then B, we've done math on this list. So for every element in range of 5, so I'm sorry, we did math on a different list that we created right here by saying range 5. You do this operation on it, and then that generates this new list. So this is using a list computation in Python, which is a great way to compress a for line into one line, a for loop into one line. It can be more human readable. It also is a little bit faster, but I'm not prepared to talk about why that is. It just, Python runs list comprehension a little faster than for loops. Okay. And here's another way of doing list math in Python. So this is what we're eventually going to do, is compare it to running these same equations in NumPy. Okay, so here we have to use the zip to create a tuple. So that way we can get the first element from A, the first element of B, the second element of A, add it to the second element of B, and go down the list and do it like that. So here we get our final result. You can see the first value, 8, is 5 plus 3, and so on. Now we can do this in NumPy a little bit quicker. So first, we make the same, an object with the same values, but this time it's a NumPy array instead of a list. And we did the same thing here to make our new object B. And you'll see that this here is also a little bit easier to understand than having to do the math to generate B and just kind of you're aiming for certain values. But here you can more concretely say, without having to do the math, that you're hoping for 5 elements. So create that, and then you're able to just add them to each other, A plus B. And NumPy knows that when you add 2 arrays, what you want to do is add element by element to those arrays. Now, if you wanted to add the arrays to each other, let me open a new tab here. Oh, sorry, I meant a new cell. So say if you just did A plus B, I guess actually up here. What it does is just append all the values to the end. So you go through A and then you go through B, and you have to do this for loop to generate this. And then NumPy, the default behavior is like what you see here with the for loop. But if you wanted to get all of the values together in one array, what you would use is a dot append B. So you append one array to the other. Actually, we need to recreate these. Let me then print our new A at the end. Oh, NumPy has no attribute end. Okay, sorry about that. I'm thinking of the wrong thing. It's concatenate in NumPy. So concatenate. Oh, why does it say is no? I think I'm going to try np.concatenate A comma B. We're going to call this one C. Oh, I have a comma there. Only integer scalars can be converted to scalar index. Okay, let me explore this a little bit more. I'm going to go back to append, but add both. Okay. So you do append numpy.append, and you don't call it on one object and add the other, which is what you would do in a list. You call numpy.append, and as arguments, you add all the things that you want to append. Okay, hopefully I didn't confuse anyone there. If you have any questions about that, again, please speak up. But I will just keep moving forward while we're here. Okay. Okay, so again, let me double check that A and B are what we intend moving forward, since I have made some edits up there. So we can also do subtraction and division, and you can see that all of these are element by element. So this one is exponent with the double asterisk, in case anyone needs a reminder of that. But this is great, but it only works if A and B are the same length. So here we're creating, we're going to create an example that's going to fail to demonstrate that. So we're creating a new B that is going to be 6 elements long. So we still have our A, that's 5, and a B, that's 6. And then if you try to multiply element by each other, you have one mismatched element. So it says they cannot be broadcast together because they have shapes 5 and 6. So just be careful and be aware that if you want to do broadcast arithmetic, it really only makes sense if they're the same length. If for some reason they're not, and you know manually that you just want to drop certain elements or things like that, you can do that. Okay. So NumPy also has constants that we can leverage. So we have pi, we have E, Euler's number. You can get these through other packages such as math as well, but it's pretty convenient that they're here in NumPy. So here we've made a NumPy range where we have range for t equals 0 to pi for pi over 4. So we're creating basically a series of radians like so. And then there's some other trigonometry that we can do. The sine, you can round the sine. So this rounds it to 3 values, 3-point accuracy. And we can also get the cosine of all these values. Okay. Similarly, we can do it all with degrees. We have this function for converting radians to degrees instead of calculating it ourselves. And this is all, pretty much the same thing. Okay, so for a refresher on indexing, we're going to take NumPy range 12. So this is going to go 0, 1, 2, 3, up to 11. And we're going to reshape it so that it is 3 by 4. Okay, so you'll notice that when you say 3 by 4, it's creating 3 elements that are 4 elements long instead of, say, 4 by 3. Now, if you just index and you ask for the 0th index, it gives you the entire first list. Let me actually, I think this should hopefully be a little bigger and easier to see. Okay. And again, you can always get the last index, like so. But say you want to pull out a very specific index, you're gonna navigate to 1, then 2. So that is, see in here, 1 and 2 is 6. Okay, so this is 0, and then this is 1. And then within 1, 4 is 0, 5 maps to 1, and 6 maps to 2. We can also get the bottom right corner with the last and the last. And you can do some slicing. So again, this is going to give us a full array, but if you say that you want to go from 0 to 4, this one you get the same thing. So this is saying that we want every element from the 0th to the 4th, well, of B, which we defined to be this. The double colons, this is just to indicate that you don't need to enter specific numbers. They have default values. And if you don't want to change the step size, you don't even need to enter the colon. You can just do 1 colon to get the whole thing. Okay. Some more on slice indexing. The third element of B, but if you go from 0 to 3, you get 2 because it's exclusive of the last index again. Okay, are there any questions so far? Would you like me to jump ahead? Anything like that? So I see that actually, Nan, you're the only person in the call right now. Can you put in the chat to confirm that you're here? Since this is being recorded, I will still carry on. So for anyone who's watching this asynchronously. Okay. So let's go back to our original array A, and we're going to show some multidimensional slicing. So if you want to go from 0 to 2, you're going to get 0 and 1 from A. Or this, you can get 0, 1, you can get every element, but you just want every other element from each row. You would do that with this colon, comma, double colon 2.
Let's get started with the GeoCat tutorial. I will be only handling the introduction part of it. So for that purpose, we would like everybody else to go to the GeoCat tutorials repository and restart their binder sessions. And I will be covering the part under this notebooks directory, which is called GeoCat. Let's get started with the overview notebook. Okay. This is, as the name suggests, the introduction to the GeoCat project. My name is Orhan Iroglu, and the GeoCat, as mentioned a few times today, is the Geoscience Community Analysis Toolkit. GeoCat is established in 2019, which was, I think, a few months before I started to work at NCAR. And we are an in-house group of software engineering people with diverse backgrounds to address NCAR's Pivot to Python initiative. So I didn't put a link to that one, but I can. No problem. I can do so maybe after this session. So NCAR's Pivot to Python was an initiative which was kind of a long decision-making process, especially in 2019, and it was for addressing, for example, the transition of NCL or similar toolkits, the legacy code bases, and transitioning them into the scientific Python ecosystem. So the GeoCat group has been formed at the time to address this need as well. I would like to walk you through the essential goals of GeoCat first. So we have three main goals, which is the development of data analysis and visualization tools for any geoscience-related purposes for structured and unstructured grids in the scientific Python ecosystem. It would be consisting of transitioning NCL functionality or implementing new functions in Python ecosystem as well. Scalability for the next generation, or as of today, maybe the current generation, geoscientific data analysis and visualization. Scalability is in the core of GeoCat implementation stack, and open development. With the term open development, we mean not only open source development, but also encouraging our community, including the contributors and user base, to get involved in any level of our project lifecycle, not only asking for new features or reporting bugs, but also getting involved in any decision making that GeoCat is doing. So I would like to show you the core technology GeoCat is making use of or heavily relying upon. So on top, you can see X-array for data input, output, and recognition purposes. And we can say GeoCat is heavily relying upon the Pangeo technologies such as X-array for data ingest purposes and Dask for scalability purposes. Other than that, we are making use of Jupyter, as many groups are doing in the same way, for documentation and exemplification purposes. And we are also making use of Numba for like just-in-time compilation. For visualization purposes, we have been for a long while using Matplotlib, also implementing some higher level functionalities on top of Matplotlib for publication quality visualization purposes. And we are also exploring and trying to starting to implement some visualization functions in the data shader stack for, especially for big data visualization purposes. So as I mentioned before, we are focused on not only structured grids, but also, especially recently, on unstructured grids, which we will cover in the afternoon. And I also put some GeoCat resources here just to give resources for self-taught activities after this event. So GeoCat is employing a continuous integration and delivery model where we are distributing our many software tools in a monthly, quasi-monthly period at the least, and in Anaconda distribution system and Python package index, PyPy. So this is all about the introduction, and I would like to show you, just before the individual parts of GeoCat starts, I would like to show you the overview or overall structure of the GeoCat project. So this is, maybe first of all, I would say, this is not a UML diagram, but for those who are used to use UML diagrams, I think it would still be useful with its own legend. It is kind of a UML diagram, let's say, but it is not exactly. On the top left, you can see the visualization part of the entire GeoCAD project, which is consisting of GeoCAD Viz and GeoCAD examples. Alia will be covering this, so I will not go through the details of individuals in this structure. On the top right, you can see the GeoCAD computational, which is consisting of GeoCAD Comp and GeoCAD F2Pi. Anissa and Heather will be covering this session in the afternoon. And GeoCAD data files for simple data housing purposes, for testing and implementation purposes. And in the bottom right, you can see the project region, which is the kind of recently awarded, which was last year, awarded project of ours by NSF, EarthCube program for unstructured grid research. And in the very bottom right, you can see the WRF Python or Weather Research and Forecast Toolkit, which we have been maintaining. The active development there is very limited because the functionality was kind of established, but we are mostly maintaining the package with user support and so. So this is all I can tell about the overview of GeoCAD project. I would like to, before I stop presenting, I would like to thank my teammates, Alia, Anissa, Heather, Philip, and Mario for putting together this comprehensive content about the GeoCAD. And I would like to thank the rest of the ESDS group for, I think, this great effort to put together this two-day event. So now I will be switching to Alia for visualization.
Is this thing on? Okay, cool. Everyone please go out to the notebooks section and select GeoCAD Viz. From there, we're going to go to the index links notebook. I'm going to close out everything we don't actually need. And this is where we are starting the tutorial. From here, we are going to first talk about the GeoCAD Comp docs. We're then going to talk about GeoCAD examples docs in more depth in the GeoCAD Comp docs. We will then cover GeoCAD visualization documentation, and then we'll get through everything else. So would you please open up in one of your tabs, the GeoCAD Comp docs. It should look like this. You will see on the left-hand side the full menu, and we will use that in the GeoCAD examples docs. I think, Anissa, are you planning on going over this on yours? Then I will save us all some time and say, this is what the docs look like, and we're going to go on and look at the GeoCAD visualization docs. Please open up GeoCAD examples docs. Really nice to have two screens here, but we don't have that right now. Okay, first, what is GeoCAD examples? GeoCAD examples are a way to share the code needed to recreate old NCL style plots. NCL was the language of choice for earth sciences here at NCAR for a very long time. We have code base going back to the 1970s. I have tried to reach out to people who wrote that and found them in retirement homes. They were quite nice, but they didn't remember what they'd done back in the 70s, so dead end. A lot of that old data that was produced by NCAR in those days, we don't have the raw data set anymore. And we want to be able to compare qualitatively for the purposes of presentation or for education, current data that we have from modern models and modern measurements that we've studied in Python, and compare that to the older data that was produced 50 years ago in the 1970s. So having the ability to directly compare plots with the same color bars, the same outline, the same shapes, have them be as similar as possible to enable the most accurate possible qualitative comparison between data sets is really, really useful, more so than you might think from a purely mathematic perspective. And that is kind of the core of GeoCAD examples. We do have some things in there that are more modern and don't necessarily have an NCL callback, but like the vast majority of the work in GeoCat examples is designed to allow this sort of backwards compatibility with older research, and allows people to switch to Python without losing continuity in their work. GeoCat visualization is similar to that in that it expands upon GeoCat examples, or in some ways contracts upon it, in that GeoCat examples is the full example of using just matplotlib, cartopy, and a few other packages. How do you make the NCL style plots? Because Python has different defaults and different assumptions about the data. GeoCat visualization is intended to remove that complexity from the end user. GeoCat visualization allows us to provide a function to an end user who just wants to produce some NCL named plot type and get data out and get a result out, a visualization out that matches exactly what they're looking for without having to worry about any of the many, many lines of matplotlib under the hood. So what visualization is intended to do is provide a single function call to the end user so they can seamlessly switch from NCL to Python. And once they have their data in Python, they simply have to call a very similar sounding function name with similar control variables to produce similar plots to what they had before. Ideally as close as possible to that original experience to make that transition less effort for people who are switching to Python, which the whole point of this project is to get people on this more scalable ecosystem. We can't do that if it creates discontinuities in the research. We just can't do it as easily. That said, let's show you what the GeoCat examples looks like. This is the home doc page for GeoCat examples. You can find that link in the section, in this top section here. You can also click, oh boy, this is sensitive. You can also click it here at the notebook gallery. We're going to start here at the top of the examples. The examples will have the gallery, some examples from GeoCat Comp. GeoCat examples is not just visualization. It does show how to use GeoCat Comp in some ways as well. It is, again, examples and not just visualization. And we have a notebook gallery that has hosted notebooks, Jupyter notebooks like you've seen today, that we will discuss in just a second, but I don't want to get too far ahead of myself. Let's start in the gallery. Again, you can get to the gallery through section 3A, small a, or just click the link from GeoCat examples, click on this little gallery icon here, or click it on the left. This gallery is a very large page that has examples of the many, many, and many plots that you can do through GeoCat examples, and includes references that call back to their various NCL counterparts, whether it be different types of color plots, contour plots, temperature plots, things that aren't really pronounceable from someone who speaks English as their primary language. How to use outlines and map projections. This comes in really, really handy if you're plotting, say, county level water usage. Sorry, the mute doesn't work on my phone. And that was an Amber Alert. So contours are really handy for plotting geopolitical data or data that can be bounded by countries. Say different water cleanliness regulations can have different effects on particulate matter in stream outflow. You can plot that based off of geopolitical region, which is the primary driver of water regulation, rather than just a raw map and have to derive what that means. Also, it's nice to have outlines of continents if you're doing ocean data, so people know where they are on the map when they're looking at a specific data point. Masking data can be important. If you have data that are primarily for, say, ocean surface temperature, you don't want to get land surface temperature data in your plot, but you might only have a raw satellite image, satellite data set that scans across the surface of the Earth, and you might have land temperature data in there. Masking will show you how to remove that data from your plot without having to go into your data set and delete the data. You can simply cover it up and not plot it. That's the point of the mask. Various different types of complicated, or complex, I should say, maps for meteorology, various different types of polygons if you want to represent data versus like a windrose, for example. That's a specific type of polygon. You might want to be able to plot that on top of whatever else. There are a lot of examples. We will not have anything close to enough time to cover them all today. So we are going to today focus on like 2 or 3 examples that show you how to use the matplot, the GeoCat examples system to either use the plots that we've provided or modify them and provide them back to us so that we can include them for other people, or just use them for yourself. I could keep talking about the many, many types of plots, but you're getting the idea at this point. So the next thing on our thing, so I don't get too far behind schedule, is the notebook gallery. So here at the very bottom, you can see we have a notebook gallery. You can look on the left right here on your screen, and we're going to click on that. And we're going to click on MPass with Data Shader and GeoViews. This is a pre-rendered notebook from a very large data set in this. I believe it was rendered on AWS. Orhan, was it rendered? Orhan is nodding. It was rendered on AWS with some fairly complicated things. This notebook gallery only has the one example thus far. Big data sets be hard to work with, yo. And what we have are the Jupyter notebook that you would need to run this very large project on your local machine. So the GeoCat examples is this repository of downloadable notebooks. Yes, it is set up as a documentation page, but here's the trick. If you scroll all the way down past the wonderful visualizations and the intense explanations of what we're all doing, you can get to the very bottom of the page and you will notice, oops, maybe not on this one. Back to the gallery, we're just going to pick a random one. You can download this as a Jupyter notebook. So you can download the examples on these doc pages as a Jupyter notebook, and that's exactly what I did to prepare for your tutorial today. I downloaded this straight off of our documentation page to make sure it would be the exact same workflow as y'all would be doing. And then from there, we are going to be running that in the notebook and modifying it as we need to explore what the different changes that we can make are. All right, what's next on the index? I don't want to get too far off track. And Orhan specifically wanted me to talk about the Taylor plots. Those were hidden somewhere, but I can just click the link. So in the GeoCat Viz, actually we should go and talk about the GeoCat Viz documentation first. GeoCat Viz docs, again, GeoCat Viz is a compacting wrapper on GeoCat examples that allow you to call GeoCat examples plots with a single line of code so that you can import your data and your data analysis pipeline into your workflow with ease, or as easily as possible with as little problem as possible. And so if you go under User API and then Routines on the left, and then you can click GeoCat Viz Plotting Routines. We're not going to talk about utility functions today because this is a visualization set. You can see how the Taylor diagram wraps a lot of parameters and functionality into a single call to GeoCat Viz Taylor diagram. This gives you a Taylor diagram plot, which the Taylor diagram is a way of modeling the reference between two variables, I believe. I was not the person who implemented this. I'm just talking about it. But like this is the sort of thing that we provide in GeoCat examples. And I think it's time to get into something more interactive than just me talking at you. Would everyone please, in their binder link, under NCL Animate 1, open up that notebook? Let's see, would you just put like an X in chat when you have that notebook opened and ready to go? All right. Okay, so first, this is directly imported from the examples documentation. I just clicked the download Jupyter Notebook link. I dropped it into the thing. I cleaned up the markdown a little bit just to make it so that in a presentation, it would not have like big long HTML links in it. But here we are. And the first thing I want to talk about is let's see what we expect to see at the end. Let's look at the original NCL plot. So if you click the original NCL plot link, that will take you to this visualization of January global surface temperature in degrees Kelvin. Aside from the existential dread that this plot brings up in most of our hearts, you can see that it is a plot of global mean surface temperature, and it has color bar at the bottom. It has the locations of all of the data sets and a color map that is not terribly helpful for people who are colorblind. All right, this has not yet been run in your binder yet, unless you've been getting ahead of me. So let's start by importing our packages. You can do that by selecting the cell and typing Shift and Enter simultaneously. Shift and Return if you're on Mac. And then we will read in the data from XR Open Dataset. Again, Shift Enter. And then we are going to create the animation. We're just going to hit Shift Enter and look at the result, and then we will go back through line by line and talk about what GeoCat Examples is doing using Matplotlib and Cartopy. You'll notice that this color map is different. We decided to choose a color map that was more friendly to people with color blindness, because as we get into modern data visualization and data analysis, it is important that we can go back to an old color map if we need to, but it's also important to show that accessibility is super, super important. Yeah, so let's start asking questions about what do you want to know about creating this animation. Is there a way for me to simultaneously see the chat and can I just borrow someone's computer or just use mine? Thank you. Okay, I can see the chat. So as I'm going along, I will be glancing at the chat, and if you have any questions, type it down, and we should be good to go. All right, so the first thing we're doing, I know we had a few people at the visualizations breakout room, but we're going to go through this line by line anyway for the people who had desire to see X-ray or DASK or whatever. So first, figure. Figure is an object class created by the Matplotlib library. The figure object contains multiple other objects called axes. Each axis or each axes object are the 2D or in some cases 3D sets of axes that hold the data and information about how to plot that data. So this figure is the outline, the canvas, if you will, upon which we'll be drawing our plots or our subplots. A plot being a representation of the data, and we're going to use figure for the outline of where the plots are going to be, and axis for the individual sets of data representations. So the first thing we're doing is we're creating a canvas of 10 by 8. I believe Matplotlib uses, is it inches or centimeters? Do we know? It's inches? It is inches. They're stuck in an imperial system, and we should free them as soon as possible. Then once we have our figure object, the figure object does have some default axes that are unpopulated. We can also create axes using plot.axes. And we are creating axes that are using the plate carré projection. This plate carré projection is just a one-to-one lat versus lon, degrees are equal length projection. It's not equal rectangular. It is also known as the equal rectangular projection. It is not equal area, nor is it equal angle. It is distorted, but it is a very good visualization for just seeing one-to-one where things are at. We are also going to import coastlines. This is a vector file, and we're setting it to line with 0.5, so it takes up less space and looks more refined on the plot. Coastlines is built into the Matplotlib Cartopy set. You can also import arbitrary outlines and things from other packages, but for now we're going to stick with the default coastlines, which I believe is a 50-meter coastline set of vectors. And then we're going to set the extent of our plot. So in theory, you could plot a subsection of the world. In this case, since we're going from minus 180 to 180 in our x direction and 90 to minus 90 in our y direction, north-south, we are going to be looking at the entire surface of the planet. And then we're going to set axis, limits, and ticks. So we've already discussed that we have set the extent of our axis, but we are calling GeoCat Viz util functions for convenience to help with this. This was a project worked on by one of our interns, and it does help a lot rather than directly addressing our axis object. Every time this can, since we pass in our axis object, it can abstract away some of the lines of code that we would otherwise need to use. And this is, again, in the GeoCat visualization package where we are doing our best to reduce the amount of total lines of code and extraneous syntax that needs to be done to create these plots. You'll notice that our lin space, so the first ones we're just providing the limits, minus 180 to 180, minus 90 to 90. In this third line, we are doing the tick marks along the x-axis. We are having a tick mark every 13 degrees. I'm not sure why that number was picked, but I think that might have just been the default that came out of it. To my knowledge, it doesn't even divide evenly into 360, but it's what was chosen. And then for our y, we are also doing 7, which, again, does not evenly just divide into 180, but, you know, do what you got to do. And then we're providing a major or minor tick every... or we're changing the size of our tick labels, it looks like. We're changing the size of the label to 10-point font, I believe. And then we add those tick labels to it using another utility function in GeoCat Viz. And again, this is all in the documentation. If you get offline, I'll come to your questions in just a second. If we got offline or you need to have a question, you can always just search the documentation for these, and that should have enough information to help you out. So I'm not changing the CRS on the DS, but on the ax. Yes, we are changing the Cartopy reprojection only on an axis because we can have multiple axes per figure, and we might want to plot the same data in equirectangular plate carré so that we can see like a relatively undistorted view that shows the polar regions well and the equatorial regions well, but that will overemphasize the area of the polar regions. And we might also want to plot it on an elliptical projection where we can see an equal area representation of, say, temperature gradients. Because if you have a abnormally hot Arctic summer and you plot that as plate carré, you're going to see way more hot space than actually exists. And that could change your intuition about the effects of what's happening. And it can lead to doubting your own results when you're doing your math if you think that your input data are more skewed one way or another than it actually is. So it might be useful to plot the same data on two different projections on two different subplots of the same figure. Kevin Rader has an important point. Yes, the 13 and 7 are probably the number of tick marks. That would make a lot more sense. Okay, when we create the initial plot that establishes a color bar, we are providing, so TAS is our data set. We are taking a two-dimensional slice of that data set. We are taking the first time step 0, and then we are taking just the 2 dimensions there and creating a base plot using the plate carré transform. The Vmin and Vmax are the minimum and maximum values, value min and value max for our data set, for our color bar. We are setting 53 levels on that color bar. We are using the color map Inferno. Inferno color map is grayscale friendly, which means that it has a brightness gradient between the lowest value and the highest value. It has a mostly single color gradient between those two values, which allows for people with different types of color blindness to still perceive the differences in brightness and in hue as it progresses, and it doesn't rely on multiple cones of the human eye. It's a good color map. I recommend using it. And then there's various other arguments that we're doing. These get into the nitty-gritty details. If you want more information specifically, just ask that in chat. Is it possible to use color brewery also? Probably. If it provides a matplotlib compatible color bar, yes. If not, making a color bar is actually relatively straightforward, although it is outside the scope of today's tutorial. So what this block does is it creates the base plot for what we are going to create the animation upon. And then we create a function called animate. This animate is something that takes in some iterative number, in this case I, and as you can see, we're calling a very similar thing to tasks, except we're passing in I, the iteration number or the time step number, along with the two-dimensional slice. So this will create our various time slices and plot them on top of our thing. Again, for each slice, we are doing the same setup using our GeoCat viz utility function set titles and labels so that each plot has its titles and labels still in place, because we are basically layering one over the other of our animation plot on our canvas. This one is not animated because this is just the straight first plot here that we get from tasks, I believe. Anissa, correct me if I am wrong. She says I am correct. I like being correct. I wish I was correct more often in college. All right, we are going to run it now. In this Jupyter notebook, we do not get an animation plotted out. At least I don't think that we do. Is there a way to call it, Anissa? Not in Binder, she says. If we're running it locally, it probably will plot, but since most of you, and including me, because of the way we're handling this setup, are on Binder, I will not show it to you. But what I can have you do is I can have you run this last block, which will save out a GIF file or GIF, depending on your level of pedantry, which will allow us to look at the output animated file and show you what the results of this Python does. Also, the GIF file will be what you would use in a presentation, say, or on a slide deck for a conference that you might want to show the animation in. This one does take a few seconds to run, so ask any questions while that is computing, please. Yeah, we'll know that it's done when this little asterisk changes to a 5. Yes.
I'm wondering if there's a way to pick the Vmin, Vmax, and contour levels automatically from your data instead of having to specify that.
I believe that if they are not set, they will automatically pick max and min. I have not tried that for the animated plots. I think the reason we set them statically for the animated plots is if you have time steps with different minimum and maximum values, that can change the color bar dynamically as the plot runs, which would make comparing time steps less intuitive, because you would have to look and reference the color bar as it changes every frame along with the frame of data, which I'm not superhuman enough to be able to do that. But I think, yes, definitely if you're doing it on a non-animated style, you don't need to provide your Vmin and Vmax unless you want to compare a color bar from today versus a color bar from a while ago, where the minimum maximum values may have changed dramatically. It has finished running. And assuming that the video is working and bitrate is sufficient, you can see that we have our working animation for a 30-day set of January global surface temperatures in Kelvin. And this is the end of the first of the 3 examples. Do we have any questions for this one? And I don't know how close I am to going over time, but I think I have 20 minutes left before lunch. Yes?
You talked about changing different map projections, or I think.
Oh, you want me to do that?
Yeah,
Sure.
like for example, with like using a polar stereographic projection, I know that there's issues getting the wrap point around. Like, so at least when I've done it, like,
Yeah.
I always have like a line. Yeah, the cyclic point. Yeah.
Oh yeah, the seam.
Yeah.
Yeah, that's always tricky. Honestly, It's why I like plate carré. But when you're looking at polar data, that seam will often be there. One way to get rid of it is to have your data plot over itself, to basically clone one, say your minus 180 as a positive 181. Because that way you get the overlap in such a way that you don't actually have any sort of gap in your plot. Although sometimes the chart wants to draw the chart border right there. And I'm not sure, that is a matplotlib thing under the hood. I'm not sure you can directly remove just one of your plot outlines. It's
think-
probably possible. Python is a Turing complete language.
I think we had a utility function for that under GeoCat Viz.
Okay.
And a number of examples covers that information. So what we can do is maybe we can put one example after the event, just for like self-taught activities.
Yeah, for sure. I mean, we have a full hack day tomorrow that we can cover it, and I
Yeah,
think
yeah.
we might have time in the schedule
Yeah.
at the very end of the day. I'm not planning on going home anytime soon.
Okay,
So.
yeah. But yeah, we can work on it tomorrow as well.
Any further questions from the chat? Nope. All right, the next one we're going to look at, we're going to skip straight to the Taylor plot, which directly uses GeoCat Viz, and we'll come back to ConOCon 6 if we have time, because I noticed that we're running a little bit long behind where I wanted to be thus far. Okay, please open in your binder link the NCL Taylor 6 Python notebook. This uses the GeoCat Viz Taylor diagram that we talked about at the very beginning, which was like an hour ago, to create a Taylor diagram. This is one of the 6 examples of how to draw Taylor diagrams. So this is the most complex of the ones that were available. That gives us the most to talk about. So again, ask questions live, and I will try to get to those questions while they are still temporally relevant. Import our packages, again, Shift Enter. And we're going to run the plot and then talk about what all of the things do. Now you'll notice that this bit of code fits on just my screen. And you will notice that the plot that it creates does not. Okay, this is what GeoCat visualization is for. It keeps the amount of code required to make complex visualizations to a manageable scale. If we were to draw out the raw amount of code done in this section here, every single time, there would be no way to reasonably talk about it in the course of the example. So let's talk about what we're doing with GeoCat Viz to make the complex visualization possible and useful to our end users and scientists who just want to get their data out. Publish or perish, and this is supposed to help you. So again, we create the figure object. This figure object is being created with some subplots. Now, subplots are similar to what we've seen before, except that the subplots are a set of multiple sets of axes. So when we call subplots, we, hang on, figure subplots. We're just in the space between subplots. We're not specifically specifying the number of subplots. Anissa, what am I missing here? Ah, where I call Taylor diagrams. Which line? Oh, here? Okay. Oh, I see. It's adding them to the thing. It's doing even more than I expected it to. I apologize. This actually, okay. Again, I'm not the one who worked on Taylor diagrams, so I apologize if I'm learning along with you. We are all fed by knowledge. We provide a list of model names. That's self-explanatory. It's a list of strings. The number of models is simply the length of that list. We create the case names. We create the number of cases, color list, labels list, and main titles list. I believe these are all passed in and then referenced sequentially in the for loop that we are going to use to generate it. For I in range 4, self-explanatory. You have all programmed at least enough to know what a for loop is. And we create some dummy data for a season. So this is not relying on genuine external data. This is relying on pseudo data to represent what the plot can do, not using a complicated import data process, because that's not really the point of the tutorial. Standard deviation, you all know what this is. This is taking the NumPy standard deviation of the data. Correlation coefficient is the other axis, I believe, of the plot. Yep. And then we are going to call our Taylor diagram. And we are passing in for DA. Our diagram object is a Taylor diagram class, correct, Anissa? And that means that we are passing in our figure object. This is the outline of our canvas. Help me out here. Rect 221? Subplot setup. 2 by 2 by? Okay. Oh, I see. Gotcha. Integer dereferencing, fun. And then the label of the things. And then we add the models on a case-by-case basis, and that's another for loop using the standard deviation of these shapes of, sorry? Oh, okay, I was just clearing through it. We add our data points to our plots and we plot them. We can go line by line, but I've lost my train of thought. I've been standing up here for an hour. Ask me questions so I can answer things. Yes, we already got to Joyt's question. Anyone else have questions right now? Before I
might say it again. Might not have heard it all.
Mhm.
Can you explain the
rectangle thing.
The question.
Oh, okay, so right. So we have a question in the chat. What is this rect 221 plus 1 plus I value? This is not something that I've used for dereferencing subplots. What this says is we are creating an integer value of 221, and then we are adding our iterative value I to that number. But what this really says is that in our hundreds place, we have the X dimensions of our subplots. In the tens place, we have the Y dimensions of our subplots. And in the final ones place of this integer that we're dereferencing, it is the element of the subplots. If there's 4 subplots, then we have 1 through 4 in that number. This is not something that I've used before, but apparently that's how we do it. And it works apparently reasonably well because you can simply add your iterator to your integer to dereference, and it will tell the background in GeoCAD visualization where to plot that particular point. Adding the legends is self-explanatory. Setting font sizes and padding. The padding that we're talking about here is the distance around all of our text, not the padding between our subplots. That padding is defined here using width space and height space values. Here being the top of the chart when I mention that. I always get frustrated when presenters tell me this or that and don't tell me where they're talking about. Adding the title, you all know how that works. And adding the model names, that takes in the name array and iteratively adds those to the different plots and elements. That's populating this small little section here in the lower left-hand corner inside of the plot boundaries. All right, we have 10 minutes if you want me to speed run Con 5 before we break for lunch. So put an X in chat if you want to speed run, put a Y in chat if you're hungry and you want to leave for lunch early. Put your question in chat if you have a question. All right, we're 1-1. All right, we're going to speed run because I'm the tiebreaker. Please open up NL Con 5 for me. This is a polar plot for those of us in the back who asked about polar plots. I'm not sure that it's the same data layout that you were talking about for your particular issue, but we'll see if it answers that question. We're going to quickly run through the import, and we're going to read in our data. We're using XR Open Dataset to pull in a netcdf data file. We're pulling that in from our GeoCat data files dataset repo. We have a repository that is used by our GeoCat examples that we can store our GeoCat examples datasets in without having to like have them be a file that you have to download. You can, if you have GeoCat data files installed in your Conda environment, you can import any of the netcdf files that are in that dataset using this syntax. That's geocat data files.get, and that will import the dataset that you want to see. This is great for if you just want to try out a bunch of different plotting techniques on data similar to what you expect to experience, and you don't want to have to import your large data set right off the bat. You can use one of the ones that we provide in our GeoCat datasets repository. Orhan, are we talking about that this tutorial ESDS conference? I'm getting a head shake. No, we are not going to talk about it later, so it is a secret that you now learned from me. You're welcome. We generate the figure, and it will produce its thing while we talk about it really quick. Again, this is not using GeoCat Viz, so you can see there's significantly more code required to produce the output. The output is this spaghetti plot of contour lines for a thing. The North Polar Stereo Projection is what this is called. And the data set that it's producing doesn't have any meaning to me. I think, is it, what is HGT 500 Monday?
It could be monthly.
Monthly, that would make more sense.
500 hectopascal.
Oh, okay, so that's like a pressure plot against of the surface, or heck,
My guess.
okay. So we have a pressure plot of like, I guess the polar vortex. Geopotential height. So we're looking at the pressure on the edge of the polar vortex here. Actually, I'm actually going to change directions real quick. Unless you have questions, showing you how to run it, you hit Shift Enter. Let me talk about the Easter egg that I put in the tutorial for y'all. So you've all heard of Google Colab, and if you haven't, now you have. Google Collaboration is a way to host a Python notebook on Google's web server through your Google Drive. And if you want to link that notebook to your friends, they can use it. But what if you have a notebook and you want to do things that Google Drive doesn't let you do on Google Colab? Well, you can open your Jupyter Lab with this command, and this will let you reference your local Jupyter server from your Google Docs collaboratory notebook. That's your Easter egg. That's the end of the presentation for GeoCat visualization. We have 5 minutes dedicated directly to questions on any topic, not necessarily what's up on screen. So ask your questions now. I spent an hour and a half talking. You have to have questions. Either I did a very good job and there are no questions to answer, or I did a very bad job and no one knows what to ask. Does anyone have a request for seeing something run or seeing something modified on an existing plot? I believe I had it up on screen for a little while, but I can just leave it up for a minute if people want to just glance at it. In 20 seconds at the top of the minute, I'm going to break for lunch, 4 minutes early. Unless there's a question to answer. Tips. On the visualized outputs point of Taylor diagram when they are far from X or Y axis. This looks like it was translated. Tips on the visualization. Okay, so what we're looking at here on the Taylor diagram is along the right axis is your correlation value with one of the cases that you're correlating against. So the elements are colored by the case of one data set. And then on the number associated with the dot, that refers to the other data set that we have. And ideally, you want the standard deviation to be low, so you want it to be toward the bottom of the plot, and you want the correlation to be as close to possible as 1. If the correlation is 1 and your standard deviation is 0, you have very accurate, very well correlated data. If your data are toward the bottom, they have a low standard deviation, but their correlation isn't very close to your reference data set, then you have an accurate model, but you don't have a precise model. Sorry, you have a precise model, but you don't have an accurate model. If you have a plot, so if you're over here on the right, where you have a very high standard deviation, sorry, very low standard deviation and a very high correlation value, then you have a value, a model that isn't very good at getting the correct answer, but is very confident in its incorrect answer. If you have a model on the left, swinging to the left, like toward the 12 o'clock noon position, then you have a model that isn't well correlated, but is precise. I think that makes that's what I'm saying? Go ahead.
Yeah, thanks. I'm wondering also if the question was about, I'm just noticing this, that some of the colored dots are outside of the semicircle. Like if you look at the spring one. So I'm wondering if I don't know if the person was asking about this, but I'm also curious, like what happens
number 4
when
on the MAM one?
Yeah, when it goes outside of maybe how to visualize points that go outside of the range.
Okay, yeah, so to do that, we would simply need to expand the axis. So right now it looks like we're visualizing from, if I had to guess, from 0 to like 1.67-ish, right? Not quite to 1.75, which would be out here, along these axes. This simply has a value, this correlation between case 4, or the PRC model, and case D, the pink model. That correlation and standard deviation are both larger than we assumed would be the general range of our correlation and standard deviation for our plot. So it's basically just the edge of a bell curve in 2 directions. And that will put it out of range. But yeah, it's if we wanted to make that fit in the plot, we would simply need to change the X and Y lengths. And I believe, yeah. We're going over time in 1 minute. What's going on, Orhan?
Yeah, so I just want to chime in as somebody who made
Please,
this plot.
please. I've been.
So the ability to plot outside of the range of the actual plot itself is actually something that came from NCL and a requirement that we were trying to satisfy to be able to reproduce NCL plots more accurately. I would not recommend plotting outside of the axes, but that's from NCL. And it
Okay.
is purposefully included to show that you can do it.
How does one engage with a GeoCat group to collaboratively contribute large dataset visualization examples? That is an amazing question, and please do so. You would go to our GeoCat examples or GeoCat visualization GitHub repositories and just open a tick, create a branch, put your development in the branch, and then just ask us for a pull request. And we'd be more than happy to work with you to get the documentation set up and do everything we can to help you help us. We are a relatively small team, and if you are willing to contribute anything to us, please come to our GitHub repositories and put the work you already do for your data visualization in a branch, or just let us know that you have data visualization tools that you would like to have included, and we will work with you to make the effort as low effort as possible.
Yeah, and just to add, if you couldn't figure out the actual work there already, so you can just go to the GitHub discussions, maybe under GeoCat examples repository, and put together a GitHub discussion, and we can move forward the things from there, right, Alia?
Yes.
Yeah.
I'll be more than happy to work with you, set up times
Yeah.
to meet one-on-one to show you how to get the branch set up, show you how to do everything. You won't have to like learn how to contribute to GitHub. I can handle that. I just need to know that you have something valuable to contribute, and then I will move whatever needs to be moved and do whatever needs to be done to get it brought in. Because if you're using it and you find it useful, then someone else will use it and find it useful, and
Yeah.
that's our whole goal. Anyone else, or are we hungry? We're hungry. Cool.
Much, and thank you very much to the audience as well. So yeah, let's head to the lunch and get full.
Yeah, thanks everybody for coming back for the afternoon. Before we jump into some more of the GeoCat content, I just wanted to take a couple minutes and preview what we're doing tomorrow. So tomorrow is going to be less tutorial focused and more about hackathons and group discussions. So Deepak and I are going to lead a sort of miniature version of the ESDS forum starting at 10:30 Mountain Time tomorrow, also in this room and online. And some of the things we want to discuss are the questions that you all filled out, the survey that you all filled out to register. And I showed this plot this morning, but you know, kind of just a teaser for some of the interesting things that we saw in that survey, which is this is just showing how familiar people are with the ESDS initiative. So hopefully this event can help increase the familiarity. We also want to talk about how we can break down barriers to participation and also get some of your real-time feedback on day one or this event in general. So I think that'll be really helpful. And then starting at around 11, we're going to form hackathon projects or discussion groups. And this is very open-ended. So if you saw the email that was sent out, I think earlier this week, there's an opportunity to submit an idea or a discussion group proposal, whatever you like. It's very open-ended, very informal. And there's a set of slides that were linked in that email. We can distribute the link in the chat as well. Maybe someone can put it in there now. And just anything that you want to propose. I know there's a couple of ideas in there already, but it'd be great to hear from lots of different folks. And then so we might get started on those before lunch, and then we'll have some more time in the afternoon to discuss. So that's all I wanted to say. Thanks for letting me jump in. I'm going to turn it over to, who's going next? Anissa.
All right, does that sound good? Better? Is that even better? Is that working? Oh, I heard it that time. Okay. Okay. All right, so I'm here to do GeoCat comp. I have slides. I don't know if they'll totally work. But so this is Introduction to GeoCat comp. GeoCat comp is the main repository under GeoCat for computational functionality. These functions are entirely in Python and are basically anything that doesn't fall into like a visualization or like I guess, data files, like has data storage or anything like that. It's all of our computational functions. And many, but not all of these functions are direct Python translations, improvements, direct translations of NCL functions. Yeah, that's the part I knew wouldn't work. So from the first slide, switching back over real quick, this is the GeoCat computational structure from Orhan's presentation. Under GeoCat comp, there is pure Python, which includes functions like climatologies and spherical. And then there is also GeoCat f2py. GeoCat f2py houses compiled language dependent, Fortran dependent functions that we didn't want to put into comp as to remove all compiled dependency from comp. By the way, you can find these in Binder. I should have said that up top. This entire presentation right here is made from this Jupyter notebook, and you can follow along by popping open that Binder link. So more specifically on GeoCat f2py, from a user's perspective, GeoCat comp will automatically include all functions housed in GeoCat f2py under GeoCat comp. If you go and you do conda install GeoCat comp, you will not have to know from a user's perspective that you are using compiled language functions. Caveat, not if you're on Windows. It doesn't quite work for Windows. But from a developer's perspective, there is that differentiation. We make these compiled language functionality under f2py with a series of Python wrappers around compiled Fortran. And on Linux and Mac, as I stated before, GeoCat comp, when installed, automatically installs GeoCat f2py underneath it as a dependency into the same namespace. So you could do geocat.comp.any function under either of the two repositories. Again, from a user's perspective, totally seamless. You don't have to worry about this at all. And now we're going to get into a little bit of documentation that Alea teased. If you're in the Binder link, you can follow along by clicking on the little link I have right here. So this is our GeoCat comp documentation. It has had a fairly major revitalization over the past few months, and that is still ongoing. So definitely continue to check back. And the structure of the documentation is broken down to for users, support, and developers. If you're brand new to GeoCat comp, there are a couple links right on this homepage that can get you started. Our getting started links looks better when you don't embed them in a Jupyter notebook, I will admit. We have kind of like an overview of what GeoCat comp is, which is kind of a short version of what I just told you guys. A quick installation, assuming you have Conda all up and ready to go and aren't using like a precompiled kernel, quick installation will give you a very brief overview of how to get started. And basic examples has some of the most basic examples that we have on the site. Thank you to Heather, by the way, who put all of this together, who will be presenting next, by the way. Yeah, definitely feel free to, if you're getting into using GeoCat comp, scroll through these basic examples, extremely like just how to use the package level stuff. There's a link to a larger installation if you're like trying to install from source, but again, I recommend not trying to install from source unless you actually need to, but all the instructions are here. And then we have our API. So our API is divided into user API and internal API. User API as a user is what you're going to want to go for. Internal API is more like for if you're going to be using GeoCat comp as a developer, if you're going to be developing functions for GeoCat comp. And then inside of here, we have kind of broken down by category, so you can more quickly find what you're looking for. Our main kind of categories right now are climatologies, Fourier filters, interpolation, meteorology, spherical harmonics, and statistics. And those are all of our pure Python functions. If we scroll all the way down, we will find GeoCat comp routines from GeoCat f2py. If it matters to you, these are all the functions that are technically Fortran under the hood, but are being wrapped in Python. And then deprecated functions. We don't need to get into those. Yeah, so this is the basic overview of our documentation. We, as always, welcome any feedback on this. And specifically, we have a whole section over here on this side, Getting Support, that links you to a variety of places to contact us, to give suggestions, ask for help. Specifically highlighted in this section. So we super duper want any involvement you can give us in this. Do you have a feature that you really want to see from NCL? Do you have a bug that you found, which if you're interested in bug hunting, this is a great opportunity. And there are several ways to reach out for our team. These are links that are, again, totally found on our documentation page, so you don't have to worry about finding this presentation again. You can submit an issue on our GitHub repository. It has nice little issue templates that you can use to get you started. You can schedule a meeting with any of us through ESDS office hours. And there's direct email that will email all of us on the GeoCat team. If you want to get involved with actually contributing to the project, we have a feature request form if you're not quite comfortable using GitHub issues. It's just a Google form that you can use, and somebody on our team will populate a GitHub issue for you. And we also have links here and in our other documentation for the contributors guide and GeoCat Comp specific contributors guide to help get you started if you want to get involved that way. All right. With that out of the way, that was this entire notebook, by the way. I'm going to get us started with just a little bit, a soft introduction into GeoCat Comp. This is basically, from a brand new user's perspective, what you can expect trying to use an NCL functionality new in Python for the first time. There's nothing fancy going on here. It's the simplest function that I could find, which is maximum daylight, the hours of daylight that we are going to get for a specific latitude, this latitude, by the way. So say you're using the NCL function daylight FAO 56, which is what this is called in NCL. This is the documentation page on the NCL documentation. And you know that this is the function that you want to use. How you would find this on GeoCat Comp is you would take your search term, the name of the NCL function up here, and if you plug that in to our search bar on our documentation, it will pull it up for you. Here is a live, bigger render of the documentation, and if I do daylight, if I can type in front of people, FAO 56, that will pull up the max daylight function for you. They do not always have the same names because max daylight we felt was way more descriptive than daylight FAO 56. But this is our documentation for max daylight. And in most, if not all, functions in our documentation that have a direct NCL counterpart, we have a C also that links to the original NCL function. So that's how you can find NCL functions equivalent on our GeoCat Comp site. So yeah, I have that here. That's the screenshot of finding it. So now that we know that we want to use max daylight instead of daylight FAO 56, I'm just going to go through an extremely basic import and use case here. So we're going to import max daylight through the geocat.conf namespace directly. We're also going to use Xarray and NumPy, I think, under here. So now we're going to calculate the max daylight hours. This is just a super basic, like what to do with like any GeoCat Comp function. So we're going to calculate the daylight hours for an entire year at latitude 40 north, which is Boulder. And that'll give us daylight hours. But this output here is probably going to be a NumPy array, and we would like to do it a little bit more complicated. We would really actually like to get this in Xarray. So what we're going to do here is we're going to do the same thing up here. We're going to wrap it in a data array, and we're going to provide it some dimensions of days and hours of daylight. This is just to give like a more slightly more advanced than just using NumPy directly. So this is what an output looks like if you use daylight hours inside of a data array with these dimensions. You see here we have probably 365 values, and each one of these corresponds to hours of daylight. And so, great, you have a 365 length array. What do you do with it? And then just at the bottom, just a tiny little visualization. We're going to use Xarray's built-in plot method here. And so with any Xarray, you can just do a dot plot afterwards, and it'll give you kind of an ad hoc visualization. So yeah, that looks exactly like we would expect. There's more daylight in the middle of the year and less towards the end. And so now you can see we did that all through GeoCat Comp. Now, for the next notebook, 02, more advanced functionality, I'm going to turn you over to our virtual presenter, Heather.
Hello. Hopefully we can get this to work. Let me share my screen. And let me enter presentation mode so that's a tad bigger for you all in the room. All right, so Anissa showed probably the most basic example that we have. Max daylight, that function is more or less a plug and chug way of using a formula, a math formula that already exists. But if we want to do something more complicated, that's not just doing a routine calculation, say we want to aggregate some data, we have lots and lots of information and we want to better understand it by making some summaries, you can also do that in GeoCat Comp. So for this one, we're going to look at some data, surface temperature data, and it's at one location. This temperature data is generated by a bunch of weather models and a model ensemble. It has data taken every 6 hours for 5 years, so that's quite a bit of information. And this is just for one data point on Earth. This isn't even for you know, a 5-kilometer resolution. But even still, this can be considered a lot if you're trying to run it locally on kind of a rinky-dink laptop. But here in Binder, we can do all of this. No matter what your system is, this should run just fine. Those are, let's hope those words ring true. So what we're going to do is we have this data. We want to, say, find the climatological averages. So in NCL, you could use a whole host of different functions to figure out what is the average monthly temperature, average daily temperature across however many years you have in your data set. And we wanted to port that same functionality into Python. So to get started, you just need data or GeoCat Comp to do the actual calculation. GeoCat data files is our repository where we hold data that we use for showing examples like this. So this is some real world data that we have hosted online. We'll also be using Xarray for similar reasons as to what Anissa was doing. And then NC time axis is an import that just makes it super convenient to quickly generate a plot when one of your axes is a time dimension. So dates rather than just say number of hours since some reference time. So we're going to do our import. And you can see it's just the same as before. From geocat.comp, we import climatology average. We'll get into that a little bit later. But first, we just want to look at our data. We just want to get this data set. So if you're ever looking for toy data to play with, GeoCat data files is a good place to go. It makes it super simple to download various files, and we have all sorts of file types, netcdf, grib files, that sort of thing. So we're going to do geocatdatafiles.get and then the name of this file, and you can see that it takes just a quick second to download. And this is where it's located on our machine. which is in the cloud. So that's why it might not look recognizable to you. It might not look like your own file structure. So now we want to look at this data with Xarray. And so super great thing about Xarray is that you can open netcdf files directly in Xarray using xarray.open_dataset and then the file path. So we're going to do that here. And what's really nice about Jupyter Notebooks is that you can see what's in your Xarray object. It prints out this nice little HTML rendering. So we can see that we have 40 different ensemble members for our weather model. We have 8,761 points on the time dimension, and then we've got some time bounds. That's not too important for this example. So that's a lot of data. Let's quickly pare that down by just pulling out data for one model member. So we will just want to use Xarray's index selection function. So that's what .icel stands for. It's selecting by index. 0 is the first index, so we just want all the data where member ID is the first member. And then we also do our dataset ds.ts because that is our data variable here. And so we're going to print that out. And this is not super easy to understand, but we can plot it. So Xarray has the dot plot capability. And this just gives us a quick and dirty plot. It's not publication quality, but it's super great to see what we have so far. So there's a lot of small scale variation in this data. You can see that there's only about 6 degrees Kelvin throughout this 5-year time period from 1990 to the start of 1996. Now, this makes sense that there's not a lot of variation. Just as a sanity check, this data is right on the equator in the middle of the Pacific Ocean. It's a pretty warm place to be, definitely better than where I am now. So there's some variation, not a lot, but there is some. And it'd be interesting to know what the average temperature is for each month in this location. And we can calculate that using the climatology_average function. So I'm going to quickly click this link and go to the documentation page. So what is super helpful about this is that you can just see exactly what the parameters are, accepted aliases for some of the parameters. These are all the NCL functions that are wrapped up in this one function. So what's really convenient about GeoCat_comp is that if we wanted to do monthly averages in NCL, we would use one of these 4 functions here at the bottom, CLM, MON, and then it has a bunch of abbreviations after that. So that's for monthly climatology. But those different functions are based on the indexes or the dimension order of your data. Dimension order doesn't matter as much in Python. We don't need to index in that way. So we can clump a lot of different NCL functions together. So that's super, super useful. And this function can do quite a bit. So we're going to get right into it. We want to do, we could do a monthly average. We could do a daily average or maybe seasonal. And I did just point this out. This is just a screenshot of the same thing. You can see that this GeoCat function replicates quite a few different NCL capabilities. So all we have to do here is we have temp, which is our Xarray dataset. And then we can use the keyword freq for frequency. And the accepted options are hour, day, month, and season. So we want month. And if we go ahead and calculate this, the first thing you might notice is how small our time dimension is now. So what this function does is it takes all of this data, aggregates it together by month. That information is actually averaged using the number of days in each month. So it does account for the fact that leap years can be involved and all that other funky stuff that calendars sometimes like to do. Now, if we want to actually look at this, we can do the same thing as before. So I have this new variable called monthly_temp, and we're going to plot that. And one of the first things you'll notice is that this data is much more granular, which is great for the purposes of what we're looking for. We want to know what months are hottest and which months are coldest. And you can see that it makes sense somewhere around July. That's when it's hottest. Now you might notice that this time dimension looks a little funky. Our data is from 1990 to the start of 1996. So why does our time dimension look like 1993 right now? And that's actually because this function, what it does is it shifts your date times to the middle of your data set. That way you can still have date objects. If you still want to work with date time objects, you can. And it just shifts everything to the approximate center of the data set. It just does the center time and then does the ceiling of that. So it picks the next year. So this is great and all, but this function can do a whole lot more than just monthly averages. Say we wanted something a little less granular. We want to see what daily averages are. All we have to do is change this frequency variable to day instead. Now, for this particular data set, we don't have a fine enough temporal resolution to compute hourly averages since our data is taken every 6 hours, but this is the smallest averaging we can do. And you can see here that the time is 365. And let's scroll through all that data and get to the plot. So really quickly, with only 2 lines, other than importing the data, we import the data, we put it through climatology average with the specifications we want, and then we can call plot, and that's it to see what's going on here. You can see particular days that were maybe abnormally cold, and you could run trends on this. You can take a deeper look at this with other functions in GeoCat Comp. Yes, in chat, Alea asked, what happens to leap year days in the daily average? So if you only have one day in your data set that's a leap year or a leap day, so only one instance of February 29th, that actually doesn't get counted. There's not enough to work with. It's not a statistically representative average, and that is ignored in this case. If you have that date show up multiple times, if I remember correctly, you can get an average for February 29th. But yeah, that is it. It's super, super simple. If you want to look more into how this function works, we have more detailed information here. So say if your time dimension wasn't named time in your X-ray object, you can pass in a string to specify that. So we don't really assume that your data is formatted or labeled in a particular way. If we do have particular formats we require, we'll put them in a notes section like this. So in this case, the data ideally should be uniformly spaced to get the best averages to make sure the weighting is done correctly. So I think we're actually pretty far ahead on time if I look at the schedule right. Are there any questions for Anissa or myself?
Hi, thanks for that. In the climatology choice that I see there's a season. Is there a way to specify atypical seasons, like not the typical DJF, but let's say I want to do, February, March, April, or something like that?
Yeah, so right now we only support the standard meteorological seasons. So December, January, February, March, April, May, June, July, August, September, October, November. We have an open ticket on our GitHub right now to add more flexibility to this so that you can calculate averages for non-standard seasons. So that is in the works.
That's also a great opportunity for contribution if anybody's interested. I know there was a question in the chat about the difference between the X-ray and the NumPy output for the first notebook, and I can go over that. Binder died. Let's see, hold on, let me get this thing back. My sincere apologies for all that noise. Hopefully this will only take a second this time.
Anissa, I actually have it already pulled up. If you want me to present it, my binder is active and working.
Oh, yeah, sure, go for it.
Cool. All right, let me reshare my screen. All right. So if we scroll back down to where we were, we can do our imports again. And all I've changed here is I'm printing out daylight hours. So this returns a NumPy array, and I can prove that by doing type, if I can actually type daylight hours. This is a NumPy ND array. And if we actually print out that information, you can see it's just a standard array, and this prints out everything. It prints out all 365 data points. If we print it out in Xarray, Xarray has an additional dimension of the hours of daylight. Actually, no, the dimensions are the same. You can see here there are 2 dimensions, 1 element per day, and then hours of daylight is this extra dimension here. The only major difference in how these print out is that this is truncated, so you don't have to see everything. It's easier to scroll through. And if you had attributes and coordinates, you could click through them. But in this most basic example, the NumPy representation and the Xarray representation are very similar, with the only addition being an extra dimension that's named.
Additionally, you could also pass in the Xarray directly. Instead of making the initial, let's see, if you could scroll back up a little bit, Heather. Yeah, the NumPy A range. If that was an Xarray instead, you would get an Xarray directly back out the first time. Most functions in GeoCat comp are set to return the same input type as they were given if they explicitly both accept NumPy and Xarray. Though I would like to note that this will be improving imminently in the next iteration that we release. Did that answer your question? I lost who asked it in chat. Yeah, okay. Are there any other questions?
I'm wondering if there are differences between the climatology function in GeoCat and like doing an Xarray group by mean. Is there other functionality that GeoCat function has that wouldn't be included if you just used an Xarray kind of wrapper function?
Yeah, so I can speak on that a little bit. And since I'm still sharing my screen, why don't we hop on over to the source for this? So I actually wrote this function, and it does rely on group by in the background. So I can actually show this to you here if we go into our repository. Let me just quick search climatology average. Oh, goodness, there's a lot in here. Okay. So in the background, this does use a lot of Xarray based things like inferring the frequency to make sure that the data is uniformly spaced and so forth. We use a lot of things like resampling and mean and dropping time dimensions. So this is actually all based on top of Xarray. The nice thing though is that what this does is it considers how to move your time dimension, and it also accounts for seasonal weighting. So if you just do group by, say for seasonal calculations, it'll just take all that data and mush it together, but not every season is the same length. Because not all months are the same length. So what this does that group by doesn't do is it right here accounts for the length of the months and does a weight for each month and then can group and sum by that. So this just accounts for some of the statistical aspects of doing this weighting. When you're dealing with date times, you have to consider how long your time periods are. Especially say if you're going from, you have one data point per month for 30 something years, and then you want to calculate seasonal averages. Well, you can't just add those 3 numbers for a season together and divide by 3. That doesn't make any sense if one of your months is, say, February, and it's considerably shorter than the other 2 months. So does that answer your question?
Yeah, thanks, Heather. It's really helpful to see the source. How did you get to the source code again from the documentation?
Yeah, so I didn't get directly to the source code. Let me backtrack. If you go up here, we have a couple options full screen to make it easier to read. You can download a particular page, but also you can go in here and these links will allow you to interact with our repository. So I clicked this first one and it takes you to the repository source. It does not take you to the direct page that function exists in. But the way our file structure is oriented is that anytime you want to look for source code, you'll go to this link right here, source/geocat, click comp, and then all of our modules that you saw on the main documentation page, those modules have the same name as these files. So if you want to see all the climatology functions, you just click climatologies.py and it'll all be in here. Both our internal functions, which are used for us developers, and our external facing functions, which don't have a underscore before them.
Thanks.
Thank you, Heather. And I just would like to make a contribution to Katie's questions. As far as I can remember, there was a very good ESDS blog post. I think most likely written by Max Grover, and maybe slightly more than a year ago. It was, if not exactly about this problem, it was about a similar X arrays group by versus actual seasonal averaging. So you can also have a look at that one as well. And yeah, what we are implementing here in the GeoCat repository is kind of the climatology specific solution. Heather, just a quick question. Did we have a comparison between what, let's say, group by would end up in a specific data set and what our seasonal climatology average would end up? I think it would be a great example to visualize the difference, potential difference. Is there any example we put together already?
No, I don't have one that's pre-made,
Okay.
but I could drum something up by the end of the day and send it out for those who are interested.
Yeah, okay. Yeah, thank you very much. And another thing, just as Katie pointed, maybe we can also implement for the documentation purposes, like quick link from each user API page to the corresponding code page in the GitHub repository. I think it will be very much useful for the documentation purposes. Thank you so much.
We can turn it to Philip early, or I can drive you all through a very in-depth GeoCat comp documentation spiel.
Oh,
I mean,
why
I'm
don't
good with going early if you guys want, but we do have like 20 minutes if you want to use that Anissa.
I've got an idea.
Um,
Why don't we go to our more complicated examples hosted on the website?
Yeah, we can do that.
I just realized it's more or less the same as the example I just showed.
It might be.
But more
Okay.
of these will be online at some point.
Yes, they will be. It's a planned thing. So as Alea described in her presentation about GeoCat Viz, There is a GeoCat comp section on GeoCat examples currently, and those examples are in the process of being migrated over into more of a GeoCat comp format. Those are accessible through the website here under usage examples. You can do a drop down. There's only one right now, mostly for testing purposes to make sure we could do it.
Hey, Anissa.
Yeah.
Could you share your screen online?
I sure could.
Thank you.
Sorry, it's on the display board and it's hard to tell when I'm not presenting. Let's see. It will not let me do that. Oh, the boxes, okay. All right, that's visible. Okay, from the top, this is where it's hosted on our documentation. Drop down right here, you can see this is the one we have currently, which I believe, Heather, is very similar to the one that you presented, as you said, and is kind of a longer form version that we made for GeoCat examples. So this example looks like this. You can scroll through it. If you're familiar at all with GeoCat examples, this will feel very familiar to you. The layout, how this goes through it. On the documentation site, these are not interactable, but you can download any page here, as Heather stated, as an IPy notebook file, and that should be usable with the correct environment. So yeah, as Heather was saying, this is the calendar average function that we go through. The imports are almost identical, except for I think we explicitly import matplotlib here. We go more in depth through reading the data, more in depth on calendar average, and a GeoCat viz style plot. These plots, as opposed to some of the ones that are coming to GeoCat Comp in the future, are directly replicating their NCL counterparts, which for GeoCat Comp documentation isn't entirely necessary. But this right here is an exact replication of the NCL example, which I now realize that I took out of this before I posted it. So you can find this exact plot on the NCL visualization, if I'm not mistaken. If there is anything that, well, obviously a lot is missing now, considering this is our only example. But if there's something that you would like to see here, this is also a very viable opportunity for a feature request. I guess it's not technically a feature, but any sort of request can go through the features or issues on GitHub, or even just email. The differences in group by, Katie, that you mentioned, that would be a fantastic thing, maybe even as an add-on to this example itself. And yeah, just knowing like what examples and like what comparisons and what like walkthroughs are going to be useful to like a user base are all something that we are definitely actively soliciting. Definitely. If you have anything, please tell us what to do. Please, please, please. And it will honestly be a really high priority for the team. I could walk through some of the ones on GeoCat examples if you'd like. Oh, please.
So I'm often comparing, like, I'm looking like at a dot where and trying to figure out where a certain times are in each of my arrays and like matching them up. But often I'm dealing with CF time versus a date time, and you can't use the where function to actually identify those because they're different times. And there's actually no way to convert between the CF time to date time that I've been able to find. And so I normally just create like a new array and reassign the attributes, but I was wondering if maybe we could have something on this to actually convert between the two calendars.
That's a great suggestion. I have no idea how to do that off the top of my head. Obviously, you've looked into it and you can figure it out. CF time makes my brain hurt. Date
Agreed.
time
Yep.
objects make my brain hurt. But yeah, that is definitely something that we could look into providing an example for here or as like a blog post somewhere. That's a fantastic request. Thank you very much.
Yeah, great.
there's lots of different calendars. So there's a lot of different calendars people use, and I was just suggesting also like things like Julian calendar as well, because we have a lot of our climatology data that's actually in Julian days.
So
that would be awesome.
you'll be happy to know that I spent a ridiculous amount of time getting our climatology and calendar averaging functions to work with Julian and Gregorian calendar and calendars that ignore leap years. Yeah, and you as the user do not have to specify anything. As long as you have a CF time or date time compliant data set, that metadata will be in with your data set, and we can pick it out, figure out what calendar you're using, and it'll adjust accordingly.
So how do I apply that?
You just have to use the function. So the only thing that is needed is if you're using an X-array data set, usually in your metadata there will be a calendar provided, either Gregorian or Julian and whatnot. And there is in the code, there is an internal function that infers the name of the calendar that you're using, so that you don't have to worry about it. It'll figure out what calendar you're using and adjust the calculation accordingly. So you
Good
just
luck.
need your calendar name in your metadata. That's all.
So would that be a good idea, Heather or Anissa, to have this as a maybe like hack case tomorrow during the GeoCat forum?
Yeah,
Okay.
I would think
Yeah.
so. What are your thoughts, Heather?
That's fine. If people want to throw all sorts of data at this and really robustly test it,
Yeah.
that'd be great. If any issue comes up or if there's a calendar that isn't supported, we can open a bug for that and get that patched.
Yeah, just for everyone else's reference. So there is going to be a GeoCat forum tomorrow. So yeah, you can come in there and we can work on this.
Are there any other questions, comments, please, or requests?
Yeah, I was wondering if you consider adding in some regrading capabilities to GeoCat, especially how to regrade, for example, the raw atmospheric cam data from CSM to the regular lat long. So I saw in the API there are some functions in the GeoCat F2Pi. I'm not sure if those are appropriate functions I should use to regrade those data.
So if you go to GeoCat comp, the routines from F to Pi, we do have a few regridding functions. I'm not sure which type of regridding you're exactly looking for, since I don't use CESM data much myself, but we do have a handful, and hopefully one of them will work for you.
I saw this one called the RCM 2 points. This is kind of, I feel like this may be a reverse of regrading lat long to cam data, because cam data is like one column and you have to regrade it to lat long, like 2 dimension. But this function looks like it's doing the opposite of what it is, but I couldn't find a reverse of this one on the website.
If you are using companion mode with the Google Meet, I have just posted a link to RCM to our grid, which takes data from a curvilinear grid, so like for WRF, and converts it to rectilinear. I'm not sure if that would work exactly for you, but that is another option.
Yeah, thanks. Yeah, I think this one may work for the ocean model. Sorry, these are very specific questions.
No, actually, those are great questions because we have a project Rygene as well. The GeoCat project is working on, and we have a package called UXarray, and there is going to be a tutorial about that today. It's in the more like initial stages of the project, not like GeoCat parts of it. So, but the regridding functionality there is significant. So what you are asking for is like from unstructured grids to structured grids regridding. And we will be especially working on that task during the UXRA implementation. So even if it is not here, you are kind of asking for like points to RCM or yeah, so yeah, I know. So we will be working on it. So just as a quick reference, UXRA is focused on data analysis and visualization functions that could be executed directly on the native unstructured grids, not like regridding, but people will still be interested in regridding to structured grids for, you know, various types of tasks. We will still be working on and providing regridding functionalities, even though our main focus is to implement functions that could be directly executable on native unstructured grids, if that makes sense. Yeah. So yeah, UXRA will be covering more on this. Alia, anything else?
Oh, I was just going to say we did a lot of recruiting tools, and I'd be happy to have that as a hackaday thing if you wanted to do it tomorrow.
But that was a great question to bridge a gap between GeoCat and UXA. Thank you for the question. Yeah. Any other questions?
All right, we could turn it over to Philip for a great transition into UXRA.
Before switching to Philip, I would like to add, all of these questions show us the pain points are common. So like regridding and the other functions. So it also shows us we are focusing on the correct direction. I'm not saying anything about, you know, the speed of the implementation, but yeah, at least the direction is looking like correct. Are you there, Philip?
Yep, just setting it
Okay.
up. Give me 1
So yeah,
second.
okay, you can take on.
Can you guys hear me fine in person and online?
Yes, in person, here's great.
Okay, so I can get started whenever we're ready. Is there any other questions for the previous one, or are we good to go?
It looks
Okay.
like from the in-person room, we are all good. And okay, yeah, mic is yours. Just get started whenever you want.
Yep. So hello, everyone. My name's Philip. I am a 2022 SciParks alumni and current Sizzle visitor here working with the GeoCat team. So today I'll be going over what UXArray is and then doing a tutorial in the second half of this presentation. So first of all the materials for this are going to be located within the same binder link for the GeoCat tutorial. If someone doesn't have access to it right now, it's okay. I'll be showing it on here. But real quickly to show how to access this, it's under the GeoCat tutorial GitHub for anyone new. And you simply just click launch binder down here and you can have the same interface as I have. So yeah, I'll jump straight into what is UXArray. So Orhan did just mention a little bit about what it is, but I'll give a kind of more in-depth description. So UXArray is a new Python package based on XArray for working with unstructured data. So I assume everyone here is at least somewhat familiar or fairly comfortable with XArray. You can think of UXArray as being not necessarily an extension, but adding more functionality to the existing functions in XArray for specifically working on unstructured data. So let's see. So if anyone here has tried to use XArray before for working with unstructured data, you probably know how much of a headache it is. The functionality really isn't there right now. It works great for structured grids, but doesn't really work with how unstructured grids are defined. So let's see. So if you're working with data from many different models, whether it's MPAS, SE, let's see. Oh, yeah, great. So structured data exists on a latitude-longitude grid where each cell is the same resolution. unstructured data, I can possibly pull something up in a second. I think there is a good visualization right here under the Rigene thing. So the picture here on the left is your standard latitude longitude grid. You can see it's a fixed resolution across the whole globe. And then these two in the center and then the far right are both examples of unstructured grids. So this one in the center, you have, I think that is a, I'm really bad with shapes, but I think like a hexagon or a, it's an isohedral grid, which just is from the MPAS model. And on the right here is from CAM-SE, it's a variable resolution grid. So unstructured grids, the main difference is they can be variable resolution. I see a lot of questions. I see some people are answering them though. But unstructured grids have variable resolution and each cell can be of a varying shape. So actually representing this in Python, I'll go into detail on this in a second, but there's more that goes into representing it other than just a latitude longitude coordinate. Did that answer your question? I see there's a couple here, but this is kind of just a good visualization of the differences between the two. So going back to what is UXArray? So like I said, it's a open source Python package and it's fairly new. So a lot of the features that we have, there may be bugs. It's not super complete yet, but we're constantly developing this and adding new features every month, and I'll touch on that a little bit later. And yeah, open development and community engagement. So we are a open source project, which means we encourage collaboration with community members. So what that means, if you're working with a specific type of climate model that it maybe doesn't work with UXArray, you can just hop on our GitHub, post an issue, make a pull request, get in contact with the developers, and we'll work on adding that feature into the package. So I can click on this link right here, the GitHub repository. Yeah, so I'm not going to go into super big detail with this, but under issues, if you have like an enhancement or feature request, you can post it here. We also have discussion forums where we discuss design features, things that maybe there's something that won't necessarily fit into a single issue. And then pull requests, if you know what you want to add to the package, you can draft one up and submit it for review. One last thing I'll cover from here is we do have a new contributors guide, which is under the documentation. This gives you a step-by-step guide of how to set up the source code, how to run it locally, do all the testing, and get things working so you can real quickly start to develop. I won't go over this in detail, but if you're interested in contributing more than just communicating with us, this is definitely a good read and shows you our whole workplace. So let's see, other than community engagement, I kind of want to highlight some main collaboration that's happening and making this project possible. So first of all is NCAR Project Rigene, which is a NSF EarthCube funded effort here at NCAR. And we're also collaborating very closely with the DOE SEATS project. So without all the great members here, this wouldn't be possible. And I just wanted to highlight that. Let's see. So I already touched on the GitHub. I touched on the Project Rigene page. Lastly is the homepage of our documentation. This probably looks very similar to if you've ever used any other Python package. You can go through how to install it, getting started, which is a work in progress, and then 2 usage examples, which will be in the second half of this tutorial. Any questions so far? I know I'm going a little bit quickly, but this is more of a overview of what UXArray actually is, and then I'll dive a little bit deeper into the tutorial in the second half.
Philip, another question, but could you please open the latest link I put into the chat?
Yep, let me.
Yeah.
Okay.
This is a presentation from a different venue, but could you please switch to the slide number 3? So yeah, I just wanted to bridge this to the question. So you can see the regrading functionality here. So yeah, we are supposed to have like implementing those regrading functions in the upcoming feature. So thank you very much, Philip. And I don't know if there's any question on this presentation as well, or any question from the room about the UXArray and Project Rigene efforts.
All right, looks like there's none in the chat. I'll just quickly mention, this is a nice diagram right here. So the whole point of UXArray is eventually we're going to also have some visualization capabilities with packages like Datashader and Matplotlib. However, right now, as you'll see in the second half, we're still in the early stages of getting all of these things working. So definitely keep an eye out for new features as we continue. And that's actually a decent segue into this last section right here, the continuous integration, continuous delivery. So kind of in simple terms, what this means is we're continuously adding and doing features throughout the month into the repository. And then at some point, I don't remember the exact date, but on a monthly basis, we release new versions of UXArray, which are available via Conda channels such as PyPy or Conda Forge. So we're continuously working on this, and you can expect at least some new features or changes or bug fixes on a monthly basis from us. Let's see, we have one question. So getting the natural earth of the CartoPy feature plotting the state boundary cultural and land features for my WRF data after installing WRF Python and GeoCat tutorial. Is that question directed towards me or towards a previous tutorial?
Are you referring to the WRF Python question?
Yeah, the most recent one.
Okay, so I already answered that one. We can, in the upcoming future, we can put the WRF Python tutorials into the GeoCat tutorials materials, because we already have a comprehensive WRF Python tutorial. But for the scope of this ESDS event, we didn't include that one. But yeah, we will be including that one for maybe self-taught activities as well as for future tutorial events.
Okay, sounds good. So if there's no questions about this section, I guess I can move on to the tutorial now, which if you want to pull it up in your binder links, everyone, I'll give everyone about a minute or two to get that ready. It's under the same directory, so it's under Notebooks, UXArray. So I'll give everyone about a minute to set that up. And then we'll jump straight into it. Can everyone put an X in the chat if they're good to go or good to continue? Okay, looks like a majority of you guys are ready, so I'll just jump straight into it. So this tutorial right here is adapted from some of the usage examples that we have in our documentation. I'll real quickly show where those are located. So here is the main page of our documentation. Under usage examples, any current and future examples will be listed here. I won't be diving into these, but the content from today's tutorial is going to be very similar to both of these notebooks. So jumping straight into dependencies, typically when you're working with this, you only really need UXArray, XArray, and for our case, we have GeoCat data files for just having a test data set. So a little bit of background information for kind of what the usual workflow looks like with unstructured data sets. So as most of you probably know, with structured data, you have maybe a single netcdf file that has all of your variables and also your grid for your latitude and longitude. For unstructured data, because of the way we represent the connectivity information and actual structure of our grid or mesh in this case, they are often stored in a separate grid file, often netcdfs, but don't necessarily have to be netcdfs. And any data variable that lies on that grid is also going to be typically in a separate file. So for this case right here, we're working with some data from the GeoFlow small project. We have a single grid, which stores our information about the structure. And then V1, V2, and V3 are each separate variables that lie on that grid. In this case, it's velocity in the X, Y, and Z direction, but that's not very important. And special thanks to John Klein, Shippy Gupta, and the Vapor team for providing us with this data set, this test data set to work with. So First thing in this tutorial won't actually be UXArray related. It'll be using Xarray to open our grid and data files. And I know probably at some point in this tutorial, I mixed up the name Xarray with UXArray. But for this section, we're going to be using some of the Open Dataset and Open MF Dataset methods from Xarray to load in our netcdf files. So here, we first import them. Let me just restart the kernel. So the first step is always to import your packages. And just like with any project, you load in, you set up your paths, and then use Open Dataset to open your files. Got to run this section. But this should look very familiar to most of you. So we can see here our grid dataset contains our mesh node X and mesh node Y, and then some extra variables: mesh node, mesh face nodes, and then mesh depth. So these follow the UGrid conventions, which UGrid conventions are used to describe the connectivity. It's a extension to the netcdf CF conventions, and it's, I think, pending approval right now, but it's used to describe and kind of have a standardized way of representing a unstructured grid. So as we can see here in our first Xarray dataset, we have all of that connectivity information. And then here we're using Open MF Dataset to combine each of the data variables into just a single data set, just for convenience. So we have V1, V2, and V3. So real quick, just to kind of sum up this section, before you do anything with UXArray, you have to use Xarray to load in your data. And that's kind of, this was a recent change that we had. Previously, we had a separate open dataset method under UXArray for doing this, but that led to a lot of confusion, which I'm not going to touch on right now. Just know you use Xarray for loading in your data when working with Xarray. So the next step is, how do we actually represent our data in UXArray? We have an Xarray object, but you probably remember in the previous section I said trying to work with Xarray on unstructured grids usually causes a big headache for a lot of users. So one of the main objects and classes that we have in UXArray is called a grid object. Grid objects, as we can see right here, take in a grid dataset, which is an Xarray dataset, and has its own method or its own attribute called DS right here. So this is our constructor right here. We can create a grid object, and then down here, it's of type UXArray grid. It's not Xarray. So you can kind of think of this object as storing all of the information that we loaded in with netcdf, but also providing some additional functionality and acts as the base for all of the other functions that we write that operate directly on the grid. So I think there's a section down here. Yeah, so grid.ds, it contains the topology, aka the information that describes our grid, and it has further attributes, variables, and functions that directly operate on unstructured grids. So yeah, going from Xarray to UXArray, at least for the data representation step, it is just a single line by calling UXGrid. And then I'll go into what we can do with this object a little bit further down, but I want to stop for a second, see if anyone has any questions, maybe any clarification is needed, or are we good to move forward? I see, David, you raised your hand.
Oh yeah, I was just curious about the standardization of the, I guess the mesh node naming, and I was just wondering, you said it was being considered for approval. Who do you ask for approval on that?
That is a great question. I personally don't know, but the web page right here, it's, if you just look up UGrid conventions, this describes everything right here. I think it's approval from, I couldn't tell you, but there's probably a big process, and it's because the CF conventions, from what I recall, are strictly for structured data, and there's nothing out there for unstructured data. And the whole point of these UGrid conventions would be having a standardized approach for unstructured data. So,
hey David, is the question about a standardized naming convention with UGrid, or standardized what?
The question was, who do we exactly go through? Like, who would we need to get approval from to actually get this to be part of the CF conventions? That was
Yeah.
the question.
Okay, so yeah, I don't have a very good answer to that one as well. I thought the question was about a standardized naming convention for the UGrid variables.
No, that we will cover in the second half of this
Yeah.
tutorial. So if we don't have, I saw there was, I think, one more hand raised, but I don't know how to use Meet very well. If let's see. Okay, it doesn't look like anyone else has their hand raised. So I will go on to the next section, which is accessing grid information. So David, even though your question wasn't directly related about this, we're going to still kind of talk about the standardized approach. So when working with UXArray, there's plenty of different conventions that our unstructured data can lie in, because there is technically no one correct way to represent unstructured data. So I did just mention UGrid, which is a fairly commonly adapted one, but there is also script, Exodus, and there's also shapefiles, which can represent our grid. So there's kind of this wild west of conventions. And what we do in UXArray is when we're loading in our data, or loading in our grid data set, behind the hood, we represent that data using UGrid conventions regardless of the original grid type in our data set. So kind of the benefit of this is if you're trying to write code that can work on many different types of unstructured data sets, you don't have to memorize all the differences between each of them. You can just work with UXArray and assume, hey, we'll be working in the UGrid conventions. And I think we also offer support for working in UGrid and then saving your data in, or saving it back into whatever format you were working with. And if we don't offer support for every different type, that's something that we always include. And yeah, this next section that I'm going to be going over is how do we actually access the data? We have this grid object, which is this very kind of abstract thing right now. We know we can access the data set, but how do we access them in a way that doesn't depend on the file format or the grid format? So here, I will real quickly show the names of the variables in our grid file, which is the same as here, but this is just a slightly different way. So we have mesh, mesh face nodes, mesh depth, so on and so forth. So one key thing to note right here is the namings here aren't exactly a one-to-one match with what the UGrid naming conventions are, which if we go into the UGrid documentation here, I'll just real quickly scroll down. I think it was this section right here. So in UGrid, what they would, for example, would call mesh 2 face X is one standard name that they use. In this data set, we have mesh node X, for example.
Philip, I
So-
would like to make a contribution here. So
Yes.
even though the examples in the UGrid conventions are referring to those names, maybe one of the strengths with UGrid convention is the flexibility with the name. So
Yep.
if you can check the documentation of the UGrid conventions, it says the namings are not being standardized. It is the reason we are both giving the flexibility to the user here, but also providing some standardization for increased convenience. So there is no naming standardization approach of UGrid convention, but we are introducing that under the UXArray implementation, just to say.
Yeah, thank you for clarifying that, Orhan. And I was going to mention, so as we see here, even though these aren't the same, like there is no standard naming convention for UGrid. There is a standard convention for what should be included in describing your unstructured grid. For example, your node X, node Y, face nodes, but the actual naming falls down onto whatever the user or researcher decides. So what we did with UXArray is we kind of we created some standard names and like a standard way of accessing these variables, regardless of what the naming convention is in the data set. So here in UXArray, we have a DS var names dictionary, which maps their original names from whatever variable we have into a standardized set of names. And these standardized names, as I was just showing like a second earlier, we just took it from how they described it in the documentation, and we said this is the standardized way of accessing it when we're using UXArray. So we have this dictionary, which can be used to map these original names to whatever the name is in the data set. And when we're accessing our variables behind the hood, we're using these attributes right here, which return a reference to the UXArray data array or data set for this specific variable. So you don't have to go through any weird indexing. You don't have to memorize any of the names or formats. You just use the standardized attribute to get whatever attribute or whichever grid attribute you're looking for. So this is what we suggest when you're working with UXArray and attempting to access the variables. However, there is a couple other ways, and this last one that I'll show kind of is how we got this feature working up here. So another way that we can access the original names is just by using the original name as an index into the data set. If this makes more sense to you than using these standardized names, the feature is there and it works exactly the same as this right here. This is a pretty typical way of accessing it. The key note though is you need to remember the name in the data set. So if you're trying to write streamlined code for something that doesn't really, it can't infer what the variable names are, using an approach like this would work regardless of what format the data set is in. And then the second one, which is what this first one is based off, is using that dictionary that I just mentioned. So you can recall a dictionary, you give it a key and it returns a value. In this case, the key is the standardized name and the value is whatever the original variable name is. So behind the hood, we construct this dictionary at the loading step when we construct a grid. And for example, if you want to access mesh2 node X and you don't know the name of your data variable, you would index your data set using the variable names dictionary with the standardized name as a key. And that applies to any of these UGrid variables. But as you can see here, this is not really the cleanest and most Pythonic approach for accessing this. So for most daily cases, if you just want to access the values, we suggest using the standardized attributes right here. Any questions about accessing data right here before I move on to some additional functionality that we have? Okay, so the last thing I have prepared for you guys today is some grid-specific functions that we have implemented. So far, we have just a couple functions that are implemented, and here that you can see that they all operate directly on the grid object, which is defined as grid right here. So for example, if we want to calculate the total face area of our mesh, we would call the calculate total face area method. Same thing for computing each of the individual face areas. We would call grid.compute face areas. So I think I should be able to run this. And this runs and computes everything. It's, I guess you can say, similar to how XArray is, where you can directly call like .mean or like any functionality on a data set or data array. For us, for UXArray, you operate directly on the grid object. So you wouldn't, if you recall from up here, we have these XArray data sets right here. So we wouldn't compute the face areas on this grid data set. We compute the face areas on the grid object, which is our main UXArray our main object for UXArray. So as we can see here, this finished loading and our total face area is that value right there. And then if we also want to check out each individual face area, we return a NumPy array of each individual face area for every face. And there's also a grid attribute. So if you've already calculated your face area before, you can simply access it and it's cached in this attribute right here. So you don't have to you don't even have to store this as a, you don't have to store it as a variable. You can still store it and access it within the grid object. So that is, I think, all we have prepared right here. I'll take any questions. And yeah, Orhan, if there's anything else you want me to cover, we have about 9 more minutes that we can utilize. David, you have another question?
Yeah, thank you. Is there any way to perform a smoothing function on an unstructured grid based on the neighbors closest to a node?
Are you asking if we have that implemented in UX Array?
Yes. Yeah.
Yeah, so I want to say it's on. So if we go into the UX Array GitHub, I have too many tabs open. Let me just go back here. So some of our planned functionality that we have here is, I'm not sure if it's on here, but something like interpolation or smoothing is something that we most likely at some point would implement. Just given how new our package is right now, we have very limited functionality other than like loading and representing your grid, because that took up a lot of our time. And as we're progressing through more iterations now, we are working on more functions like that. Orhan, if there's maybe more you would want to add for that specific question. Hopefully,
David, are you asking for example, you have vertices that show your individual faces with their nodes within them, and are you asking about if we can generate an unstructured grid topology from that vertices?
I think so. I'm thinking of just some kind of way of working on the unstructured grid without going into a lat long interpolation and essentially getting a smooth version of the unstructured grid.
Yeah, I think, if I'm understanding the question correctly, yes, we have. So if you have a simple NumPy array in the form of like vertices list, then yes, you can generate an unstructured grids from that. That's correct, right, Anissa? Okay, yeah. Philip, could you show us the grid object constructor user API?
Yep.
Maybe you can use the documentation.
Oh yeah, that'll look a little bit cleaner. Let me pull that up right here.
So user API, and let's see. Okay, so yeah, if you can check here, David, the init function, which is the constructor, that data set could be an X-array data set, or it could be just a simple NumPy array, which would be your like simple list of nodes under list of faces. So you can just skip the complicated X-array part if you think so, and you can just generate your unstructured grids with those list of faces within each list of nodes. So is that an answer to your question?
Maybe it points me in the right direction. So
yeah, okay. And please feel free to follow up maybe tomorrow during our user discussion forum, or through our GitHub repository, maybe via a GitHub discussion or issue, then we can follow the things from there.
Thank you.
Yep, if I can add one thing as well, David, I think we both may have slightly misinterpreted your question, but you mentioned that you wanted to perform, let's just say, some operation on the unstructured grid without needing to interpolate or downscale to a structured grid. Is that more akin of what you were asking?
Yeah, I don't even know if it's theoretically possible.
It is, and there are algorithms that exist for directly doing stuff like means or face areas on unstructured grids. And that is one of the main motivators for us creating this package, is we want to provide functions for the user that run all of these algorithms that X-Array already has implemented for structured grids, but directly on unstructured grids, if it's possible. some things may not be possible for unstructured grids, but there are algorithms and different approaches that we are adding functions as we go for that. So you wouldn't need, once you load in your unstructured data, if it's possible on unstructured grids, we would have a function that works on the grid object that would perform that operation for you, and it wouldn't need to represent it as a structured grid behind the hood. It would directly operate on the unstructured grid. So that is still a work in progress. We are adding more functions as we speak. So definitely keep an eye out to just our monthly releases. And if there's anything specifically, anyone here, not just you, David, that there's some functionality that's already existing in Xarray, but doesn't work on unstructured grids, this is a great topic of discussion for our GitHub issues or our GitHub discussion page. So again, we are very happy to engage with the community and get feature requests that way, because it's one of the best ways that we can add features that users will actually use. So hopefully that answered your question more. And then we have 3 more minutes before we go on to a break. Is there any other questions from anyone here in the chat? Otherwise, I will. Let's see. Are curved linear grids also classified as unstructured grids? That is a great question, and I think just by looking at it, a curved linear grids, I want to say, Orhan, correct me if I'm wrong, but I want to say possibly.
Yes.
It's not.
Yeah.
I
Like,
would.
The question is like, the curvilinear is structured or unstructured grids, right?
Yeah.
So yeah, curvilinear, I think we can say it is a structured grid, and through the GeoCat functionality, you can regulate the curvilinear grids to unstructured grids, or as we mentioned in the previous section, in the future, with the regulating functions to be implemented in the UXarray, you will be able to perform a conversion in the, or regrading in the reverse direction, like from the unstructured to curvilinear grids. And I would like to say one more thing here, not in this specific question, but in general. The current code structure you have seen today is the result of the design choice we have been doing so far, but we are both in need of and already receiving perspectives and feedback from the people or user with more science background. So we are really in need of such perspective to finalize this design choice here. So we will have a discussion forum tomorrow, and you are more than welcome to attend us, join us to have a discussion there about the code structure to see if we can bridge any gap between structured and unstructured workflows, for example. Philip, thank you very much. So
yeah, we had one more
yeah,
question
sure.
in the chat. I'll quickly
Go ahead.
to this. So the question was, is UXarray the appropriate tool for taking county level data in the US and transforming it to a 0.5 grid to compare with climate model output? So I would say down the line, yes, it would be appropriate. Currently, we don't have, I think, the regridding functionality implemented in UXarray, but assuming your county level data lies on an unstructured grid, which if it's counties, they can be represented using in an unstructured grid if you decide to do that. Eventually, if that is an unstructured grid and you want to convert it to a structured grid, we would have support for that down the line, but currently we do not. Hopefully that answered your question, and I think I will pass it back to Orhan and we can have, I think, a 15-minute break. Again, thank you guys. If anyone has any other questions, feel free to reach out and communicate with on the GitHub repository with us.
Thank you very much. And actually, we are already over time, but I just would like to show one more thing here, if I can share quick my screen. Okay. going to the X-ray. Was very quick, and I just would like to show one thing here, which is I think Philip didn't show as far as I can remember. So under the repository, if you go to the documentation page, which is like docs directory, and if you can click under the user API, you will have a draft UXarray API documentation. And if you can check that, we have put the comprehensive today's and futures function list under this documentation. And you are more than welcome to input on this document because it is a tentative list of future functionalities that we are planning to implement under UXarray. It doesn't mean we are going to implement them as is in the current list. So if you can input them, input to this list, we can consider modifying any function or adding or removing any function here, which you can kind of compare with the user API documentation Philip already showed you. So yeah, this is the future list. So it can give you a better understanding of what we are planning in the future for UXarray implementation. So that was all I wanted to add. Thank you very much, Philip, and thank you very much to all of you.
Okay, so starting over, sorry about the hiccup. So my name is Stasia Roshinsky, and I'm going to be giving a talk on our new visualization tool called just the Vapor Python API. So you may be familiar with the Vapor 3 GUI application. It's a tool for analyzing earth sciences data. And so it specializes in specifically this earth sciences data, and that makes it very easy and intuitive to use for that data. So whenever it has built-in support for many data formats and common visualization types that you might want to perform. So this is just an example of what the GUI looks like, but we're going to be focusing on a showcase of the Python tool, which essentially what this tool does is it exposes all of the capabilities of the GUI in Python, so it can be used in Jupyter notebooks or just regular old Python scripts. Okay. So here I have a Jupyter notebook where I have kind of a demo of kind of the basic capabilities that you might want to use using this this new API. So to begin, of course, we're just importing the API. Let me reset reset this thing. Okay, so so your visualization in Vapor is based around sessions, and this kind of allows you to have multiple multiple visualization sessions open, and the session contains the entire state of your work. A major advantage with this system is that it integrates with the Vapor GUI. So you can have a session that you have been working on in Python and open it in Vapor GUI, and vice versa. So you could start working in Vapor, have a visualization, then save that session, open it in the Python API or in your Jupyter notebook, and everything will look exactly the same. Or you can start working in a Jupyter notebook, save your session, and then open it in Vapor to further your efforts. And I'll be demoing that later. So to begin, we're going to create a session with just instantiating a new Python object here. And we're going to be loading a data set. And this is a simulation of Hurricane Katrina. And it's a WRF simulation. So we specify that it's a WRF file, and we pass in this function here kind of just passes a list of WRF files that I have on my computer. So Vapor has built-in support for many common models and data formats such as WRF, MPAS, CAM, UGRID, CF compliant, NetCDF, among others. So if you have any of these data formats and you import them into Vapor or the Vapor Python API, everything will automatically work out of the box. You won't need any additional configuration. So we have our data, and I'm going to go into more depth, but kind of just to get things going, we can just start and visualize something right away. So I'm going to create a new volume. I do this by taking my data that I got from opening the data set, and I create a new renderer, and I pass in that I want a volume renderer. This gives me an object that references this volume renderer. And then I'm going to set the variable name to QCloud, which is a variable that I already know I have in my data. But later on, I'm going to kind of show you how you can inspect this using the Vapor API. And then I'm going to create a visualizer widget. And this is kind of a Jupyter widget, which lets you interact with your data in interactive, I guess interactively. It's kind of redundant, but let me run this. And then I'm going to display the widget. And as you can see here, we have our volume. However, it is fully opaque because we haven't specified the hiding of your data. So we have this very simple function here. So we take our volume object and we get the primary transfer function with this function here. And that gives us the transfer function for the volume. And I can set this opacity list. So here I'm kind of setting an arbitrary opacity ramp, and that's useful for exploration. However, it also supports specifying specific control points at certain data values, setting opacities for different data values. So if I run this cell, as you can see in our Jupyter notebook, right away we have this volume rendering of the QCloud variable. Let's say we want to add a map, a georeferenced map to this visualization. It's as simple as creating an image renderer, which is the same thing called data new renderer and renderer.image renderer. And this will if your data is georeferenced, which this data set is, it will pull up one of the built-in maps that Vapor comes with. And as you can see here, we have a map of the Florida coast, of the Florida Gulf over here. So that's kind of like a quick demo. Let's see. So once you have your visualization, you can go ahead and, so this is kind of just like an interactive thing. But if you actually want to get an actual rendering, you would call session.show. And this pretty much takes your viz window and creates an actual image. However, if you want to save it to the disk, you can call session.render, and that will also create a PNG on the drive. And if we go in here, you can see we have that PNG file that was just generated. You can also use Vapor you can also use the API to actually explore your data sets. Here I have some kind of very simple examples. We're going to get a list of so we can query from the data object. We can get the time coordinate variable name, number of time steps, coordinate variables, dimensions, among others. So if I run this, you can see it'll just dump out all that information about the data set. And this isn't kind of the raw data. This has kind of already been pre-processed by Vapor using kind of its routines for reading in different data set formats. And here I'm going to quickly dump a few of the just a few of the first 2D and 3D variables. So if I'm going to loop over the dimensions and then get data var names, pass in the dimension, then just cut off the first few. So if I run this, as you can see here, we get the first two 2D variables and then associated coordinates, dimensionality, data ranges, etc. And this can be useful, obviously, for visualizing later on. So another thing you might want to do with your data is simulate and render a flow advection. And once again, this is extremely simple with Vapor. So all we do here is we create a new renderer with a flow renderer parameter. And then we set the field variable names. So since we're passing in two 2D variables, it's automatically going to configure everything for a 2D flow advection. And all we do is we're going to go ahead and just show this rendering. So we run that, and right away we have the flow advection. And there's obviously many ways to configure this. I have kind of a few things I want to cover, and depending on time and interest, I can go more in depth on any of these specific topics. Let me actually quickly just make this a little more uniform here, or I could just do. Anyway, another common visualization technique is bar rendering. Also, once again, simple with Vapor. All you do is create a new renderer with a bar renderer. We're going to set it to be a 2D bar renderer, setting the field variable names again, and this is kind of just like a configuration for the rendering itself. And as you can see, right away we have some barbs, and we can still do anything we want with this. We can launch the visualizer to use it to view it interactively. We can save this, etc. Another common thing is pseudocolors. So this is done with a 2D data renderer. So we kind of do the same thing. We create a new renderer with the 2D data renderer. We set the variable that you want to render, U10. And here I'm kind of just configuring another thing for the visual fidelity, setting the map value, and we show this cell. And as you can see here, we have the 2D pseudocolor of the U10 variable with the map behind it. So Vapor has various color maps built in. We have a whole host of them. I can quickly, if I pull up annotations, you can get a list of them. This notebook, which is included in Vapor, in the distribution, will give you a list of them. And I don't know what it's doing. I guess it's not running it. That's okay. Hopefully it does not mess up this one here. But here we're going to go ahead and change the and this is all documented online, and also this is documented in the distributed example. So we're going to change it to a Kindleman, and you can see that was immediately shown here. We'll remove this renderer. So Vapor also supports a whole host of annotations that are also easily enabled. Here in this case, I just have one example. Once again, this is something that I have a whole demo on that. If someone's interested, we can go into more depth on this. But I'm simply going to enable a time annotation, which displays the current formatted timestamp. And this is because next we are going to render an animation using the time steps. So this data set that I opened has about 40 time steps in it. And we can animate this this volume over the time domain by so we can create an animation. So this is obviously also not completely necessary. You could simply use the previous render image and change the time step to save a sequence of images and then process that as you would normally. However, this animation utility class makes this a lot easier. And that's kind of the idea behind this whole package, is letting you do these things quickly and easily. So we create an animation. You're just setting the number of time steps you want to render, because we don't have time to render the whole data set. And I'm going to loop over all these time steps. So we're going to set the time step on the session. Here we're so one of the things is this is a moving domain data set. So these kind of 3 lines here kind of account for that. First, we're going to view after the time step is changed, the domain will move. So we're going to tell the camera to view everything and center the view. And then also Vapor preserves the current region of interest when you're of your renderers. And that's because if you have, say, a moving domain, you might want to look at a specific region, and you want that region to stay constant even as your domain moves. But in this case, you kind of just want to see the entire data set. So we have to reset the region of interest at each time step. And then we're going to call animation.capture frame. And this is kind of simple little thing that'll show a progress bar. So when you run this, and now it's rendering everything in the background. And here we have a little some progress going. So once that is finished, as you can see here, we can do many things with this. We can either show it. If we just call show, it'll pop up a video in your Jupyter notebook. If you run show interactive, it kind of pops up a more custom widget that lets you have more control over the animation you just created. So you can slow it down or set the specific frame. And if we play it here, you can see that we just animated our data set essentially. And also it also has built-in video encoding. So all I have to do is just, we can call save MP4 out.mp4. We run this cell and it has encoded that, that animation as an MP4. So if you go into our work folder, we have this out.mp4 and you can see the animation here. And once again, if we show that visualizer that we created earlier, we can explore the current state of the notebook and end it in the session. And there's obviously more controls here you can do. So I want to make, before I continue, I wanted to have a quick aside on documentation. So currently this comes with two forms. When you install Vapor, it comes with two forms of documentation. One is this collection of notebooks that goes over many of these concepts in depth. But the primary form of documentation is actually built into Python. So if you have a question about anything that you're working with, all you have to do is just call this built-in function, this built-in Python function help. And this can be called either on an object, or so for example, if I have this animation, this anim, I could call help on this anim and it'll display all the help for that. Or you can call it on a class. So here I have it on the transfer function class. And as you can see here, you get all of your documentation and functions and arguments, etc. And now I'm going to kind of demonstrate one of the coolest features, which is the how this integrates with the Vapor GUI application. If I run this this cell here, which saves the current session in a session file, I can actually go ahead and open Vapor, which I have installed here. And I can open this session file. I go into and as you can see here, we have the exact same state that we have here in this in the Vapor GUI, and we can continue working. We can kind of, it's a lot easier to say work with the transfer function, and then you can go the other way. You could do some work here, save the session file, and then reopen it in Python and continue working there. So this is all good, but also if you want to use NumPy or Xarray, this API also supports that. So here I have an example of each. If I go ahead and I open this NumPy example, what we do here is we can the same thing. We import Vapor, we create a session. So this time we create a Python data set. So there's a distinction between regular data sets and Python data sets. The Python data sets don't fully work with session files, and that's because they depend on state in the Python interpreter. So if you're creating Xarray and NumPy data, it would be kind of difficult to figure out which data you specifically want saved, and you need reference later and writing that all to disk. So these aren't compatible for importing into Vapor, but it still lets you use the full power of the Vapor API. So if I can go ahead here and just create a arbitrary NumPy array, and on the Python data set, we can add NumPy data and give it a variable name and the NumPy array. So here you have the NumPy array printed. And now we're going to go ahead and just create a wireframe renderer for this variable we just created here. And then we're going to show it. So here we have the same kind of visualizer session that we had earlier. And you could have all the capabilities that you had for the actual data for this. And here, similarly, we're using Xarray. And this allows us to kind of have all the advantages of Xarray. So you can have, so here we're generating a curvilinear 2D grid, and also and giving it some random data. And this time we kind of have the same process, but instead we do add Xarray data and pass in the Xarray variable here. And then same thing, we're going to create a wireframe renderer and show it. And as you can see here, we have the X-ray data plotted using Vapor. So I guess going forward, there's a few other things I could cover, but I was kind of wondering if anyone had any questions, if there was any topics anyone would want me specifically to cover. If not, I kind of have more I could talk about, or also I don't have to. Yeah.
Do you have any control over the camera perspective using the API?
You do. So there is a camera API, so I can go ahead and just write help Vapor. I think it would be off the top of my head. Wrong capitalization. So I spelled that right. I spelled it wrong.
You have that so much set as
Oh, I didn't realize that was the thing. There we go. Yeah. Let's just do. It's easier if I have this open. So there we go. So here we have the camera API. So the session you can query. So actually over here in the first example, we did use the camera API. In the animation, we're calling session.getCamera, and then we're calling view all, which simply kind of figures out the best perspective to view your data. However, there's a whole host of controls, as you can see here. You can set manually the position target up. So you can set all the camera parameters manually, or you can do things. You have like a lookup function, look at function, which is also very simple to use. You can zoom, etc.
A question about the camera get position and get target, or I guess set position and set target as well. Is the coordinate system for the camera the same as the coordinate system for the data, or is it a second coordinate system for the renderer?
So it is a separate coordinate system. I think we are currently working on adding lat long controls and essentially using data set controls for the. So I guess it depends really. If your data set has a projection. So if your data is say in lat long and it has a projection, then it will use the projected coordinate system. If your data does not have a projection, then it'll use the data set coordinate system. But we're going to add functions to the camera module that allow you to use your data set coordinates, and it'll automatically do the reverse projection and place it in the correct location.
Thanks. This is super interesting. My question kind of has to do with when do you read data from disk, and it's motivated by the fact that I tend to work with X-ray, and I read, I don't know, touch 2000 netcdf files to construct like a Dask array, so it's lazy. Could I just plug that in to your X-ray example, or should I think a little more closely about subsetting my data first because you're going to load it all into memory?
Sure. So if your netcdf data is CF compliant, then I'd recommend just loading it directly using the dataset functionality, because we have built-in support for netcdf data. So if you have the correct annotations, it'll automatically set up your coordinates, everything right away. And then also that'll load everything lazily. So it'll go through your data to compute metadata. So actually, in this example, the data set I'm using is like it's like a 40 time step WRF simulation. That's like 10 gigs. As you can see, it opens the whole thing in, I don't know, like 2 or 3 seconds, because it kind of only reads the information it needs to calculate metadata, and then it'll load the data on the fly, and it also keeps a cache of the information you need. So if you do a rendering and then you render something else, you don't need the data you had previously, it'll kind of flush out the cache with the information you don't need and just read stuff from disk as you need. But if you're using X-ray, because of that kind of issue I was talking about earlier, where it depends on the Python interpreter state, there really isn't a guarantee, especially in Python, that for the lifetime of the data. So kind of the only way is when you create that data, it has to copy it over, because there's no guarantee that it won't be there later when it needs it. But if that's a use case that's necessary, there could be an option. If you could open a support ticket for passing in, say, more of like data pointers, where you would have to, as the user, guarantee that data is still there, but then it wouldn't actually need to keep a local copy of that on the API side. Mhm. Yeah.
When rendering surfaces in the renderer, do you have the option to provide materials to those surfaces, or is it just color at this point?
It's so depending on the renderer. Actually, it's easy if I just open this here. So you don't have full material support. Also because a lot of the renderers are implemented using just I put this just like custom OpenGL code. So we don't have like a unified material system like you would in like say a game engine like Unity, but you do have controls over say the lighting parameters in addition, like for some renderers. So here you can kind of configure the the shininess, the kind of these are like Phong rendering parameters.
Okay, so you're using Phong rendering. Are you also doing, is it a volumetric ray march, or is it some other way of getting semi-transparent data?
It's a ray march, yeah.
Can you set the parameters on the ray march, step length, that kind of thing?
You can. Not directly, just because we find that I think for most users that'd probably be just
Too
confusing.
granular, yeah.
Yeah. But you can set kind of essentially the sample rate scalar, but it kind of a lot of effort was put into having kind of it intelligently figure out the proper rates for everything.
Depth of field, is that a possibility, or?
So we currently have, like I said, most of the rendering is done with OpenGL, just through custom code for everything. However, we are currently working on integrating a ray tracer and a path tracer using Intel Osprey. And you actually have this here. Yeah, so you can enable Osprey. Currently, it only works for the volume renderer. But ideally in the future, we're going to have kind of a unified system where you'll be able to run all of your renderers through a path tracer and get depth of field, shadowing, all the fancy bells and whistles.
Cool. Follow-up question on the lighting. You said you're using a Phong renderer. When you're placing your light source, does the user have control over the light source location, and or is there a one-button solution to, say, put the sun where it should be relative to the map at the time?
Currently, we do not. So the way that I believe, I think, I don't even know if we have, I think we might have light source controls, or at least we used to. I'm not familiar at the moment. But currently what it does is it places the light source at the camera. And that's just kind of the point of that is it gives you contouring without having to worry about lighting. So you always have some sort of 3D contouring from the lighting without having to configure anything.
Possibility for a second light source, you can see shadows and edges and have a little bit more depth, or?
That's definitely something we'd add when we have the path tracer, but also just with some of the GLSL code, it's kind of reaching its complexity limit when it comes to the compilers and what they can handle.
Thank you.
There is one more question from Matt Remy in the chat, Stash. Matt says, maybe you already said this and I missed it, but can you open the viewer, render windows from an interactive Python session in a shell, or is it required to be run with a Jupyter notebook?
Yeah, so the interactive part of it is required to be run in Jupyter, and that's because you need some sort of windowing or GUI system to do this. And if that's, hypothetically, we could add something where it would launch a GUI application from the terminal, but for now, it specifically uses the Jupyter front end for that. Yeah. All right. Yeah, I guess so. So then let me. So first of all, I would like to thank to the all audience and presenters for today for the great effort and their time to make this happen.